15 years elapsed without a single alteration. Then, abruptly, Earth's established protocol for extraterrestrial engagement underwent a complete overhaul. A singular stipulation now dominates. No communication is permissible without the explicit endorsement of the United Nations. This revision surfaced mere weeks prior to the anticipated closest approach of the interstellar visitor, designated 3I Atlas. The alignment of these events is too conspicuous to disregard. The pronouncements carry an almost scripted cadence. Was this meticulously orchestrated, or are we observing veiled apprehension amidst scientific circles? Because announcements of this magnitude do not materialize by chance. Stay with me, for by the conclusion of this presentation, you will comprehend that the pertinent inquiry is not whether we are preparing for contact, but rather who has already facilitated it. If the enigma of 3I Atlas has captivated you as profoundly as it has me, please ensure you indicate your approval and subscribe to receive every update as this narrative unfolds in real time. Share your location and local time in the comments, along with your conviction regarding the complete transparency of these world-altering discoveries. Part 1. The Prohibition Clause and 3I Atlas, an explosive revelation. Envision this scenario. You are perusing a scientific treatise on a Tuesday afternoon, and nestled within the 7th page, you encounter a solitary sentence that reshapes everything. Pending the outcome of appropriate international consultations, no reply shall be sent to a confirmed extraterrestrial intelligence. This is it. 20 words, devoid of fanfare or a formal press conference. Simply a quiet regulation inserted into the revised draft of the SETI post-detection protocols, published on ARF in late 2025. For context, ARF is the official repository for the Search for Extraterrestrial Intelligence Institute. You might dismiss this as mere administrative housekeeping, the sort of tidying up scientists undertake every decade or so. You would be mistaken, for herein lies the crux of the matter. That draft was disseminated concurrently with the astronomers' announcement of 3I Atlas, the third confirmed object of interstellar origin ever observed entering our solar system. It originates not from the Kuiper Belt, nor the Oort cloud, but from an entirely unknown region. This celestial body was first observed on July 1, 2025, by the Atlas Survey Telescope in Chile, exhibiting velocities that definitively indicate its extrasolar genesis. Its closest proximity to our Sun, its perihelion, is scheduled for late October of 2025. As of this moment, 3I Atlas has already traversed the orbit of Mars, approaching us with a velocity that renders conventional solar system objects virtually stationary. Permit me to pose this question. Why would a directive explicitly forbidding any entity from transmitting a response to extraterrestrial intelligence suddenly appear in an official document, just as an interstellar visitor is entering our celestial neighborhood? Is this timing remarkable, or merely a fortuitous coincidence? Retain that query. Let us rewind and clarify the practical implications of responding to extraterrestrial intelligence. We are not discussing abstract philosophical discourse or theoretical brainstorming sessions. We are referring to the physical transmission of a message, a radio pulse, a laser emission, any signal that could be construed as deliberate communication originating from Earth. Under the prior guidelines, in effect since approximately 2010 or earlier, there was counsel suggesting consultation and coordination, but no explicit prohibition preventing an individual or organization from initiating contact. The language was more permissive, with terms like should and may, allowing for latitude in interpretation. However, this new draft employs the term shall. This is legal terminology, an imperative, not a suggestion. Now consider this. The preceding major revision of these protocols had not occurred in over a decade. This is not a routine undertaking. The International Academy of Astronautics, the governing body responsible for these guidelines, does not alter them arbitrarily. They convene committees, host symposia, and solicit input from the global scientific community. The fact that this revision was finalized in 2025, incorporating this specific clause concerning responses, and coinciding with the emergence of 3I Atlas in the public consciousness, creates what one might term a perfect convergence of timing. New protocols, an interstellar object, global attention, widespread speculation. 3I Atlas is not just another piece of cosmic debris. It is the third interstellar object we have verifiably detected, following 1I Oumuamua in 2017 and 2CI Borisov in 2019. However, unlike those prior visitors, 3I Atlas arrives during a period of unparalleled observational capabilities. We now possess the James Webb Space Telescope, and the Hubble Space Telescope remains operational. We have ground-based observatories equipped with polarimetric and spectroscopic instruments capable of dissecting the object's composition with a precision unattainable 5 years ago. And the findings are, well, we will elaborate on that shortly. Suffice it to say, the data is sufficiently unusual to command significant public and scientific attention. Consider this scenario. Imagine you are part of a private SETI research initiative. You have spent years scanning the heavens, hopeful of intercepting a signal, a technosignature, anything indicative of non-terrestrial intelligence. Then one day, you detect something. Perhaps it is a radio burst originating from the direction of 3I Atlas. Perhaps it is an optical flash. Or maybe it is an anomaly within the infrared spectrum that defies explanation by any known natural phenomenon. Under the former regulations, you might have had the discretion to reply, to transmit a message stating, "We perceive you. We are here." But under the new protocol, that option is no longer available. You are obligated to inform the relevant authorities, securely archive your findings, and await further instructions. Await consultation, await the United Nations deliberation, await the convergence of diplomats, jurists, and ethicists to arrive at a consensus regarding whether humanity should engage at all. Who has the prerogative to speak first? This is the question the protocol now addresses. And the current answer is no one. Not until universal accord is reached, or at least until those in positions of authority concur. This represents a fundamentally altered stance from our previous approach. Allow me to be unambiguous. Many will assert that this is merely administrative procedure. They will argue that the International Academy of Astronautics is simply modernizing antiquated guidelines to reflect contemporary technological advancements and geopolitical realities. They will emphasize that the protocols have consistently underscored international collaboration, and they are not entirely incorrect. However, the clause itself, the explicit prohibition on responses, the use of binding terminology, this is novel. It fundamentally redefines the entire framework for any future contact scenario. It shifts the focus from should we respond to who decides if and when we respond. This regulation is not concealed within classified archives. It is publicly accessible to anyone with an internet connection. But how many individuals have actually perused it? How many comprehend its implications? And more critically, How many realize that this rule is already in effect, poised for invocation the moment a triggering event occurs? Thus, our path forward is as follows. Over the subsequent segments, we will meticulously examine the revised protocol, dissecting it word by word. We will reconstruct the chronological development and the timing of its release. We will scrutinize the peculiar circumstances surrounding 3I Atlas, the interstellar entity that appears to have arrived at precisely the opportune moment to lend relevance to this protocol. Furthermore, we will investigate the reactions from various quarters, ranging from mainstream scientists to those disseminating theories from their residences. Because if this rule is presently operative, and if a detection is made today, tomorrow, or next week, coinciding with 3I Atlas's closest approach, then we must ascertain who commands the narrative. Are we being prepared for silence? Part 2. The precise content of the revised protocol. The document bears the title, SETI Post-Detection Protocols. Progress towards a new version, authored by Garrett and his colleagues, and published in 2025 on ARIV. It is neither brief nor straightforward, but to grasp the magnitude of the recent changes, a thorough understanding of its contents is imperative. Therefore, let us dissect it section by section and compare it with its predecessor. Firstly, the scope has broadened significantly. The prior protocols, from 2010 and earlier, were primarily concerned with radio signals. This was logical at the time, as radio was the principal medium for SETI endeavors. However, the current draft acknowledges that technosignatures can manifest in diverse forms, including optical lasers, waste heat from megastructures detected in the infrared spectrum, anomalies in polarimetric data, and even particle emissions that deviate from natural models. The definition of detection has expanded beyond a simple celestial beep to encompass any indicator suggesting the presence of technology, whether intentional or not. Secondly, the verification procedures have been intensified. Under the former guidelines, upon detecting an anomaly, confirmation through independent observation was encouraged, but the process lacked formal rigor. The revised draft mandates multiple independent verifications from distinct observatories prior to any public disclosure. It stipulates the archiving of both raw and processed data within tamper-proof storage systems. It specifies that the frequency bands utilized for detection must be shielded from interference. These are not recommendations, they are mandatory requirements. The objective is to preclude erroneous alarms and ensure the authenticity of any announced discovery. Thirdly, data dissemination and open access have been formalized. Once a detection is verified, the data must be made available to the global scientific community. No proprietary claims or data withholding. This is a direct response to concerns that arose following the observation of Oumuamua, when certain data was initially restricted or delayed. The protocol aims to ensure transparency, at least among the scientific fraternity. Whether this transparency extends to the broader public remains an open question. Fourthly and critically, the protocol establishes an International Academy of Astronautics Post-Detection Subcommittee. This body comprises not merely astronomers, but a multidisciplinary team encompassing scientists, legal experts, ethicists, and communication specialists. Their mandate is to orchestrate the response, advise on the content and recipient of communications, and determine the opportune moment for dissemination. They effectively become the central nexus of the decision-making process. If you are contemplating who controls the narrative, their role is central. And then we arrive at the clause that initiated this entire discussion. No reply shall be sent to a confirmed extraterrestrial intelligence pending the outcome of appropriate international consultations. Let us contrast this with the preceding language. The 2010 version, if it addressed responses at all, utilized phrases such as should consult or may consider. The transition from should to shall represents a profound shift. Should implies advice, shall signifies a command. The new protocol unequivocally states that no single organization, governmental entity, or individual possesses the authority to respond on behalf of humanity without extensive consultation. This consultation, by implication, would involve the United Nations, specifically its Committee on the Peaceful Uses of Outer Space. Now here is a crucial detail that is often overlooked. The protocol is advisory in nature. It is not a legally binding international treaty. It does not, at present, possess the force of law. The document itself describes it as a living document, implying its capacity for evolution in response to changing circumstances. However, the potency of advisory documents lies in their adoption. When a sufficient number of governments and institutions regard the protocol as authoritative, it effectively assumes the status of law, even in the absence of a formal treaty. Given the considerable influence of the International Academy of Astronautics within space policy circles, this is a distinct possibility. Allow me to present a hypothetical scenario to illustrate its practical ramifications. Imagine a private SEAT-E consortium, perhaps based in Silicon Valley or Finland, detecting a clear and undeniable signal. It undergoes verification and is confirmed as authentic. Under the former regulations, they might convene a press conference or even contemplate sending a reply, perhaps something to the effect of, "We have received your transmission. Here is ours." However, under the new draft, this course of action is prohibited. They are required to notify the International Academy of Astronautics Subcommittee. This subcommittee will then review the data, convene meetings, and consult with the United Nations. Weeks, perhaps months, may pass. During this interim, the group responsible for the detection is legally and ethically obligated not to respond. They must wait. And the outcomes during this waiting period are uncertain. Other nations might respond covertly. The signal might cease. A crucial opportunity might be missed. The protocol extends its purview to even seemingly minor details that hold significant implications. For instance, it mandates that all detection data be archived in formats resistant to tampering. It requires that frequency bands designated for SETI operations be protected from terrestrial interference, necessitating coordination with telecommunications regulatory bodies. It even addresses the need for protocols governing public messaging, including how announcements should be framed, how public expectations should be managed, and how panic should be averted. These are not merely scientific guidelines. They constitute governance frameworks. They anticipate not only the scientific aspects of detection, but also the subsequent political and psychological ramifications. Therefore, when individuals refer to this as a routine update, inquire as to when routine updates have begun to fundamentally redefine the authority to represent the human species. Since when have they incorporated explicit prohibitions on communication into what were previously considered best practices? This is not a superficial change, it is structural. The question of whether to reply or not to reply has transitioned from the domain of philosophy into that of official policy. And this policy is embedded within a comprehensive governance structure that dictates not only the content of our communications, but also the decision-making body responsible for them. Now, for the uncomfortable aspect, the protocol presumes that detection will occur through official channels, via recognized institutions with established credibility. But what if this is not the case? What if detection arises from a crowd-sourced project, from amateur astronomers, or from an entity operating outside established systems? The protocol attempts to address this by mandating notification, but it cannot enforce compliance. This is where ambiguity arises. If an individual or group detects something and chooses to respond irrespective of the protocol, what are the consequences? Will the international community condemn them? Will governments intervene? Will we witness conflicting messages being dispatched into the cosmos, some authorized, others unauthorized? The protocol offers no definitive answer, perhaps because it is incapable of doing so. However, it unequivocally clarifies one point. The era of individual or institutional autonomy in this domain has concluded. If a detection is made, that information no longer belongs to the discoverer, nor do they control the response. The protocol has collectivized the decision-making process. Whether one deems this prudent, necessary, or perilous depends on the degree of trust placed in the institutions now vested with this authority. Regardless, the landscape has fundamentally shifted. Part 3. A forensic examination of the timeline. How long has this been in development? If you harbor suspicions regarding the timing, you are not alone. When juxtaposed, the emergence of a new protocol and the arrival of an interstellar object invariably provoke the question, were they aware? Was this a hasty endeavor spurred by 3i Atlas? Or is this confluence merely coincidental? To ascertain this, we must meticulously trace the timeline and observe how the pieces align. Let us commence at the origin. The initial Declaration of Principles Concerning Activities, following the detection of extraterrestrial intelligence, was formulated in 1989. This represented the first formal attempt to establish guidelines for humanity's actions in the event of receiving a signal from another civilization. The declaration articulated fundamental principles: verify the detection, notify relevant authorities, publicize the discovery, and coordinate international responses. It was aspirational, more of a philosophical statement than a legal framework, but it marked a beginning. In 1995, a supplementary protocol was introduced, specifically addressing the matter of responses. This document acknowledged that replying to a signal was fundamentally distinct from detecting one, and advocated for international consultation before any reply was dispatched. However, once again, the language was conciliatory, suggesting consultation rather than mandating it. Furthermore, there was no enforcement mechanism, no dedicated subcommittee, no formal process. It was guidance, not governance. Fast forward to 2010, and we encounter what is often referred to as the streamlined version. This update consolidated previous documents, clarified certain procedural steps, and brought the protocols into alignment with advancements in radio astronomy and international space law. Nevertheless, even at that juncture, the primary focus remained on detection and notification. The question of response was still regarded as secondary, something to be addressed should it become relevant. Then, in 2022, a shift occurred. The International Academy of Astronautics SETI Committee initiated discussions regarding a comprehensive revision. Meeting minutes from that year indicate the committee's sentiment that the existing protocols were outdated, particularly in light of technological progress in detection methods and the increasing involvement of private entities in space exploration and SETI research. They sought a protocol capable of addressing not only radio signals, but also optical technosignatures, infrared anomalies, and potentially even physical artifacts such as interstellar probes. They also desired more explicit guidance on the matter of responses, as this issue had become more contentious as more individuals began seriously contemplating active SETI. The revision process was protracted. Drafts were presented at the International Astronautical Congress in 2023 and 2024. Feedback was solicited from the global scientific community. Revisions were implemented, and then, in late September or early October of 2025, the draft was made publicly available on AREV. This is the document under examination, the one containing the prohibition clause. Now this is where 3I Atlas enters the narrative. The object was discovered on July 1, 2025, by the Atlas survey in Chile. Initial observations confirmed its trajectory was hyperbolic, indicating an origin outside our solar system. By mid-July, astronomers had calculated its perihelion for late October, around the 30th. Media coverage began to escalate in August as additional data became available from Hubble, JWST, and ground-based observatories. By September, 3I Atlas had become a prominent headline. Consequently, the timeline appears as follows. The protocol revision process commenced in 2022, well before any awareness of 3I Atlas. Drafts were circulated internally in 2023 and 2024. The object was discovered in July 2025. The protocol was published publicly in late September or early October 2025, precisely as media attention surrounding the object intensified. Does this sequence suggest that the protocol was expedited in response to 3I Atlas? Not necessarily. The revision process adheres to a predictable pattern: committee meetings, conference presentations, public comment periods, final drafts. These undertakings require years. One cannot hastily construct a comprehensive governance framework in a matter of months, especially one involving multiple international bodies. The timeline indicates that the protocol was already in development, and its publication serendipitously coincided with the discovery and approach of the object. However, herein lies the complication with this explanation. We lack precise knowledge regarding when the no-reply clause was finalized. Was it part of the 2023 draft, or was it incorporated at a later stage, perhaps in 2024, or even early 2025? The public documentation does not provide this specificity, and this informational void permits speculation. Because if the clause was added subsequent to the discovery of 3I Atlas, then the timing appears less coincidental and more reactive. We possess no definitive proof either way. We have a timeline that is suggestive, but not conclusive. There is an additional perspective to consider. Scientific endeavors often remain inscrutable to those outside the field. Committees convene in private, and drafts are circulated among a select cadre of specialists before public dissemination. Consequently, even if the amendment process commenced in the year 2022, it's conceivable that particulars, including the stipulation regarding a response, were subjected to deliberation and refinement, right up to the ultimate release. Should such discussions have been ongoing in the middle of 2025, coincident with the emergence of 311 Atlas, the decision to incorporate that specific wording might have been swayed by the celestial body's approach, irrespective of the overarching amendment being planned years prior. Herein lies what we can assert with certainty. The protocol was not hastily assembled. The evolutionary path of this revision is historically documented, extending back a minimum of 3 years. However, the synchronicity of its public unveiling, precisely as an extrasolar body nears our Sun and commands global attention, is undeniably striking. Whether this confluence of events signifies happenstance, astute foresight, or something more profound hinges on the degree of faith one places in the involved organizations. And this leads us to an unspoken query. If the protocol was not expedited due to 3 Atlas, then why does it feel that way? Perhaps it is because the object itself prompts inquiries that the protocol appears designed to address. Perhaps it is because the advent of an interstellar visitor, particularly one exhibiting peculiar behavior, renders the prospect of contact less theoretical and more immediate. Or perhaps it is a consequence of our inherent inclination to discern patterns and forge connections, even when those links are tenuous. Nevertheless, the salient point is this: even if the timing is coincidental, the protocol remains valid. The relevant clause persists, and 3I Atlas continues its trajectory. Thus, irrespective of whether the two are interrelated, we are on the cusp of witnessing the ramifications when regulatory frameworks intersect with the cosmic realm. This revelation promises to be engaging, regardless of how the temporal sequence unfolds. Part 4, 3 Atlas, the celestial visitor that intensified headlines. Let us now turn our attention to this visitor. 3 Atlas is not merely another fragment of cosmic detritus. It represents the third confirmed celestial entity originating from beyond our solar system, following in the wake of 1 I Oumuamua in 2017 and 2 I Boros in 2019. However, in contrast to its predecessors, 3IE Atlas makes its appearance during a golden era of astronomical observation. The instruments at our disposal today surpass those available even 5 years ago, and these advanced tools are revealing aspects of this object that deviate from conventional expectations. This body was initially identified on the first day of July, 2025, by the Atlas Survey, a network of observatories engineered to detect near-Earth objects and potential impact threats. The acronym ATLAS itself, standing for Asteroid Terrestrial Impact Last Alert System, underscores the primary function of these instruments: spotting celestial bodies that could pose a risk to our planet. Yet, on this occasion, they identified an object incapable of impacting Earth, its origin lying far beyond our solar neighborhood. Its trajectory was immediately recognized as hyperbolic, signifying a velocity too great to be captured by the Sun's gravitational pull. It originated elsewhere, and after its passage through our system, is destined to return to interstellar space. The details of its orbit are extraordinary. Its closest approach to the Sun, termed perihelion, is projected for approximately the 30th of October 2025, at a distance of roughly 1.4 astronomical units. This places it within the orbital path of Mars, close enough for detailed observation, yet not so proximate as to present any hazard to Earth. Following perihelion, the object will continue its outward journey, making its nearest approach to Earth sometime in December of 2025. By that juncture, it will be receding from us at speeds precluding any possibility of pursuit with current technological capabilities. We are afforded a singular opportunity to study this entity, and that moment is unfolding presently. So, what are our findings? That is precisely where the situation becomes intriguing. The James Webb Space Telescope has been meticulously observing 3 Atlas since the latter part of July. The data it has transmitted is, to employ a mild descriptor, unusual. Spectroscopic analysis indicates a coma predominantly composed of carbon dioxide, with a carbon dioxide to water ratio approximating 8:1, plus or minus 1. This ratio is exceptionally elevated. Most comets, even those originating within our own solar system, exhibit the inverse ratio. Water typically constitutes the primary volatile component, with carbon dioxide playing a secondary role. However, 3 Atlas inverts this established order. The reason remains unknown. It may have coalesced within a unique molecular cloud, possessing a distinct chemical makeup compared to the Genesis cloud of our solar system. Alternatively, other phenomena may be at play. Further insights are provided by the polarimetry data. Observations conducted by ground-based telescopes reveal a pronounced negative polarization branch, signifying an atypical pattern in the way light reflects off the object's surface or coma. The angle of inversion, the point at which polarization reverses its sign, hovers around 17 degrees. This is a characteristic that astronomers have not previously encountered in comets, suggesting that the constituent materials of the object, or the particulate matter being ejected from it, possess properties that do not align with any recognized cometary analogues. Again, these observations could be attributed to exotic but natural chemical processes, or they could indicate something else entirely. Adding to the intrigue are more speculative claims. Certain reports, primarily from less reputable sources, have posited that the object is releasing metallic compounds, specifically nickel alloys, at a rate of approximately 4 grams per second without detectable ionization. If substantiated, this would be remarkable, as naturally occurring comets do not expel metals in such a manner. However, these assertions remain unsubstantiated, derived from preliminary spectroscopic data that has not undergone peer review or independent verification by other observatories. Therefore, a degree of caution is warranted. While captivating, these claims do not constitute definitive evidence at this juncture. Moreover, there is the question of the object's behavior. Initial observations noted an absence of a pronounced tail, which is atypical for a comet approaching the Sun. Comets characteristically develop tails as solar radiation heats their surfaces, causing the release of volatile substances. However, 3 Atlas was initially quiescent. Subsequently, in late August, the KEK Observatory detected what is termed an anti-tail, a phenomenon oriented towards the Sun rather than away from it. Anti-tails, while uncommon, are not unprecedented. They arise when larger particulate matter is expelled from the comet, lagging behind its orbital path and creating an optical illusion. Nevertheless, when considered in conjunction with other observations, the anti-tail contributes to the perception that this object is behaving in ways that elude our complete understanding. Thus, we arrive at the hypothetical scenario. Could these anomalies be explained by natural mechanisms? Absolutely. Celestial bodies from other star systems originate from diverse cosmic environments, potentially possessing compositions previously unencountered. The elevated carbon dioxide ratio could be indicative of formation within a colder, denser region of a molecular cloud. The polarimetry data might reflect the unique characteristics of its dust grains. The metallic emissions, if factual, could be a consequence of some exotic surface chemistry yet to be identified. Natural explanations exist for all observed phenomena. However, What if these explanations are not natural? What if 3I Atlas represents something else entirely? Perhaps a probe, an artifact, or a construct dispatched by an extraterrestrial civilization to explore other star systems, akin to humanity's own probes, Voyager and Pioneer, venturing into interstellar space. If this were the case, the timing of the protocol revision would gain significant plausibility. For if it were known or even suspected that an interstellar visitor might be artificial, establishing protocols for response would be paramount. A framework for decision-making would be essential, ensuring that no precipitate actions, such as unauthorized transmission of messages, were taken. To be clear, the majority of scientists examining the data continue to favor natural explanations. The prevailing scientific view, if one can be called such, posits that 3 Atlas is a comet, albeit an anomalous one. However, consensus does not equate to irrefutable proof, and the available data remains incomplete. We are still within the observation window, and new data continues to arrive daily. Until a comprehensive understanding is achieved, definitive exclusions cannot be made. Nevertheless, this much can be stated. 3 Atlas stands at the nexus of scientific inquiry and speculative conjecture. It is the sort of event that challenges our fundamental assumptions, expands the frontiers of our knowledge, and compels us to confront uncomfortable questions. Regardless of whether its origin is natural or manufactured, mundane or extraordinary, the object is already serving as a practical test case for the very protocols under discussion. For if this is what the universe presents when we are not actively observing, what will transpire when our attention is focused? And that question, more than any specific data point, is why 3I Atlas holds significance. It is the reason for widespread observation and the reason the protocol revision feels so prescient. Because whether the object is a cosmic snowball or a piece of alien engineering, its arrival conjures precisely the kind of scenario for which the protocol is devised: detection, verification, consultation, and subsequent response or non-response. The structural framework is established. Now we must ascertain whether it will be adhered to. Part 5, Immediate Reactions, Scientific Live Streams, and the Social Feed. The narrative surrounding 3I Atlas is not confined to academic journals and official press releases. It is unfolding across platforms like YouTube and Twitter, and in live broadcasts hosted by individuals from their own residences. The interpretations being constructed within these forums diverge considerably from those emanating from NASA and the European Space Agency. This is the arena where the contest for public perception is being waged, and it is a tumultuous affair. On one side stand the authoritative scientific voices. NASA's blog entries prioritize caution and ongoing investigation, with phrases such as "no threat to Earth" and "still under analysis" forming the core of their communications. The European Space Agency has issued a frequently asked questions document to address common misconceptions regarding the object. Their tone is measured, designed to reassure, and perhaps even deliberately understated. The underlying message is unequivocal. This represents intriguing scientific exploration, not a cause for alarm. It is a comet, an unusual one, and it is being studied. The implication is that further attention is unwarranted. On the opposing side resides the alternative media landscape. YouTube channels bearing monikers such as Cosmic Secrets and Classified Truth are generating a profusion of videos with titles like "Alien Probe Confirmed" and "They're Hiding the Truth About 3I Atlas." These productions garner hundreds of thousands of views, interspersing clips from official press conferences with ominous musical scores and drawing parallels between the protocol revision and the object's arrival. The underlying insinuation is invariably consistent. The authorities possess knowledge they are deliberately withholding. This, they suggest, is not merely a comet, but an elaborate deception. Allow me to provide an illustration. One prominent live stream host, reacting to the protocol revision, stated, "When there is nothing to conceal, information is disseminated organically. But this document, this is effectively a gag order. It signifies their intention that if anything transpires, if we detect something, if an individual observes something, they will be prohibited from discussing it without authorization. And that authorization originates with the United Nations. Seriously, do you genuinely believe the UN will apprise you if extraterrestrials materialize?" The host further characterized the prohibition on unprompted replies as indicative of preemptive control, a stratagem by governments to monopolize the narrative before any other party can voice their perspective. And here is the crucial point. That argument resonates with a substantial segment of the populace because it contains an element of truth. The protocol does indeed centralize decision-making processes. It mandates consultation prior to any form of response. And if one is predisposed to skepticism regarding established institutions, if one already harbors the conviction that governments routinely suppress information, then the protocol appears less like judicious governance and more like a confirmation of one's deepest apprehensions. Social media has served to amplify this divergence. Memes depicting the protocol document alongside images of Three-Eye Atlas are circulating widely, accompanied by captions such as "they knew" or "coincidence? I think not." Hashtags like Dutch Alien Probe and Zlakgegorder are trending, interspersed with more sober discussions concerning cometary chemistry and orbital mechanics. The discourse fractures into distinct echo chambers, each reinforcing its own particular viewpoint. Scientists engage with fellow scientists, while conspiracy theorists converse amongst themselves, leaving the average individual attempting to ascertain the truth caught in the crossfire. However, what is particularly fascinating is that both factions are drawing from the same reservoir of information. Both are scrutinizing the protocol document. Both are examining the data transmitted by JWST and Hubble, and both are cognizant of the established timeline. Yet, they arrive at entirely disparate conclusions. The reason lies in the fundamental nature of the questions they pose. Scientists are inquiring, what does the collected data reveal about the object's composition and origin? Conversely, conspiracy theorists are asking, why is this information being disclosed now, and what vital details are being omitted? The former question seeks factual information, while the latter probes for underlying motives. These are fundamentally distinct modes of investigation. Consequently, where does this leave us? The protocol has now become a focal point in a broader cultural debate concerning trust, transparency, and authority. For the scientific community, the clause mandating no unauthorized reply signifies prudent restraint, a measure to prevent humanity from undertaking any reckless or uncoordinated actions during a moment of profound historical significance. For those harboring skepticism, it represents an instrument of control, a mechanism for restricting access to information and stifling independent voices. Both interpretations are internally coherent, supported by selective readings of the same documents, and are actively shaping public perception in ways that will prove consequential should something truly extraordinary be detected. The question of credibility looms large in this context. Whom do you choose to believe? Do you place your trust in NASA, with its decades of exploration and peer-reviewed scientific achievements? Or do you rely on an independent researcher broadcasting from their basement, unburdened by institutional constraints? Do you accept the official explanations at face value? Or do you suspect they are sanitized versions of a more complex reality? These are not easily answered questions, nor do they possess straightforward solutions, given that institutions have, at times, withheld information, and independent voices have, on occasion, been demonstrably mistaken. What is beyond dispute is that the identical text of the protocol is fueling two markedly different narratives. The scientific narrative posits that existing procedures are being updated to align with contemporary technology and international collaboration. The narrative of suspicion suggests that a framework is being erected to control the story before it breaks. And both narratives are being amplified by the arrival of 3I Atlas, an object sufficiently enigmatic to serve as a blank canvas upon which individuals can project their hopes or fears. Herein lies the uncomfortable verity. The contest for public perception is already in progress. And it is not being waged through factual evidence. It is being fought with framing, with rhetoric, with imagery, and with emotional appeals. The outcome of this struggle will dictate how individuals respond should something genuinely extraordinary be identified. Will they place their faith in official channels, or will they seek out alternative sources? Will they subscribe to the scientific explanation, or will they embrace the conspiracy theory? The protocol may dictate who speaks on behalf of humanity, but it cannot dictate whom individuals choose to listen to. And that perhaps represents the more significant challenge. Therefore, as 3 Atlas approaches perihelion, as further data becomes available, and as the narrative continues to unfold, ask yourself this: which narrative are you choosing to embrace, and for what reasons? Because the fundamental question is not merely, what is 3 Atlas? The question is, who controls the narrative, and who controls the contact? And the answer to that query may reveal more about humanity itself than about the object hurtling through the cosmos. Part 6, Technological Signature Expansion, Our Detection Capabilities and Limitations. Now, when most individuals contemplate SETI, or the search for extraterrestrial intelligence, they envision a radio telescope directed towards the stars, engaged in the act of listening for a signal. This mental image is not entirely inaccurate, it is simply incomplete. This is because the spectrum of phenomena we are capable of detecting, the signatures that might indicate the presence of technology, has expanded far beyond the realm of radio waves. The protocol update from 2025 reflects this broadening scope in ways that fundamentally alter what we are searching for and how we would react upon discovery. Let us commence with the foundational principles. A technological signature, or technosignature, is any observable phenomenon that suggests the existence of technology. Traditional SETI efforts primarily focused on narrowband radio signals, as these are not generated through natural processes. If one detects a signal precisely at 1.420420 MHz, the frequency associated with neutral hydrogen, and this signal exhibits tight focusing and modulation patterns indicative of informational content, it is highly probable that something artificial has been identified. Natural processes do not produce narrowband signals. Instead, they generate noise, which are broadband emissions spanning a wide range of frequencies. Consequently, for decades, SETI was virtually synonymous with radio astronomy. Listen for a distinctive beep and hope for its repetition. However, technological advancements have coincided with a more sophisticated understanding of what might constitute a technosignature. The 2025 protocol explicitly acknowledges this by broadening the definition of detection to encompass optical and infrared laser pulses, evidence of megastructures such as Dyson spheres or Dyson swarms, particulate emissions that deviate from natural models, and even polarimetric signatures that could imply artificial constructs or materials. These are not mere figments of science fiction. They are phenomena that can be investigated using current or near-future technological capabilities. Optical SETI, for instance, is dedicated to searching for brief, intense bursts of laser light. If an extraterrestrial civilization sought to attract our attention, they might transmit a pulsed laser signal, powerful enough to momentarily outshine their home star. Our telescopes are equipped to detect such emissions. Projects like the Optical SETI program at Harvard have been monitoring for these types of events for years. While no definitive findings have been made to date, the technology itself is mature and functional. If a signal is being transmitted towards us via laser, we possess the capacity to perceive it. Infrared investigations are focused on detecting waste heat. Every civilization that utilizes energy inevitably generates waste heat as a byproduct. Should a civilization achieve a level of advancement where it harnesses a significant fraction of its star's energy, perhaps through the construction of a Dyson sphere or a swarm of solar collectors, that structure would emit radiation in the infrared spectrum. While the James Webb Space Telescope was not specifically designed for the detection of alien megastructures, it could identify them if they exist. The Wide Field Infrared Survey Explorer, known as WISE, has already compiled a catalog of billions of infrared sources. Astronomers are diligently sifting through this data in search of anomalies, entities that are excessively luminous or possess structures that cannot be attributed to natural causes. Particle and ion sensors are capable of detecting charged emissions originating from objects traversing space. Comets, for example, release ions when their surfaces sublimate under solar radiation. But what if an object emits particles in a manner inconsistent with natural comets? What if the elemental composition is anomalous, or the rate of emission is aberrant, or the distribution pattern is unusual? Such deviations are potentially detectable. Furthermore, if the emissions include industrial compounds, such as refined metals or synthetic molecules, the implications become even more significant. Polarimetry measures the manner in which light is scattered from surfaces or dispersed through particulate clouds. Different materials exhibit distinct light-scattering properties. Natural comets scatter light in predictable patterns, dictated by the size and composition of their constituent dust grains. However, if an object's polarization signature does not align with any known cometary analog, it serves as a red flag. This does not confirm artificiality, but it necessitates more rigorous investigation. And this is precisely what we are observing with 3 Atlas. The polarimetry data is anomalous. It does not conform to established patterns. While anomalous does not automatically equate to artificial, it does compel a more thorough examination. However, a significant challenge lies in the inherent limitations of detection and the potential for false positives. Natural phenomena can, in surprising ways, mimic technosignatures. Pulsars, for instance, were initially misinterpreted as alien beacons upon their discovery in 1967. Their signals were so regular and precisely timed that astronomers briefly entertained the possibility of an artificial origin, even humorously nicknaming the first detected pulsar, LGM-1, for Little Green Men. However, subsequent analysis revealed a natural explanation: rapidly rotating neutron stars. No extraterrestrials were involved. The challenge persists across the board. Stellar bodies encircled by nebulae of particulate matter can emit thermal radiation that could be mistaken for the residual warmth of a manufactured sphere. Celestial wanderers might exhibit trails composed of unusual molecular structures if their chemical makeup is exotic. Brief, intense bursts of light can be generated by tumbling celestial rocks, their surfaces reflecting solar radiation in a manner that creates transient, luminous events. For every potential indicator of advanced civilization, there exists at least one natural phenomenon that must first be excluded. This underscores why the established procedure emphasizes corroboration from multiple sources and independent validation. Should you observe something peculiar within one band of the electromagnetic spectrum, it is imperative to examine it across other bands. If a single observatory notes an anomaly, confirmation is required from additional observatories. It is necessary to retain the raw observational data, allowing other researchers to conduct their own analyses. One must also dismiss terrestrial interference, reflections from orbiting platforms, instrumentation malfunctions, and errors in computational algorithms. The array of possibilities that can produce misleading signals is extensive, and each must be systematically eliminated before one can confidently assert a significant discovery. Now consider the implications of this for 3I Atlas. We possess data from the James Webb Space Telescope indicating an atypical ratio of carbon dioxide to water. Furthermore, polarimetry readings reveal a characteristic unlike anything previously observed. There are also unsubstantiated reports of metallic compound emanations. Individually, each of these findings could be attributed to natural causes, such as unusual chemical interactions, peculiar dust particle compositions, or measurement inaccuracies. However, when viewed collectively, they form a discernible pattern of deviations that is difficult to disregard. This is precisely where the landscape of detection becomes intricate, as we navigate a nebulous territory situated between phenomena definitively natural and those potentially artificial. The vast majority of cosmic observations are unequivocally natural. A minuscule fraction may hold the possibility of artificial origin. Differentiating between these categories presents an exceptionally formidable task. The established protocol endeavors to address this by mandating a comprehensive, multidisciplinary strategy. Do not confine your inquiries to astronomers. Consult with chemists, material scientists, and engineers familiar with spacecraft design and the observable signatures of artificial constructs. Engage statisticians capable of determining whether a pattern is truly aberrant or merely a product of random fluctuations and observational bias. Assemble a team equipped to examine the data from every conceivable perspective before formulating any conclusive statements. However, there is a speculative consideration that deeply concerns many. What if an object crafted by an advanced civilization is intentionally designed to evade detection? What if its intended appearance is that of a natural object upon initial observation? If you were dispatching an exploratory craft to another stellar system, would you desire its artificial nature to be immediately apparent? Or would you prefer it to blend seamlessly with its surroundings, appearing as a comet or asteroid until it had gathered sufficient intelligence or chose to disclose its presence? We ourselves engineer spacecraft with reduced detectability in mind at times. Stealth satellites exist. Reconnaissance probes are a reality. Why would another civilization refrain from employing similar tactics? If an object deliberately mimics natural signatures, our current detection apparatus might prove insufficient to identify it without exceptionally meticulous scrutiny. This is where the broadened scope of techno-signature identification becomes paramount. If our search is limited to radio transmissions, we might overlook laser pulses. If our focus is solely on visible light wavelengths, we might miss subtle infrared luminescence. If our measurements are confined to bulk composition, we could fail to detect nuanced isotopic ratios that deviate from any recognized natural processes. The greater the number of investigative methods we employ, the more challenging it becomes for an artificial entity to remain concealed. Consequently, this brings us back to the protocol. With expanded definitions of technosignatures, the no-reply stipulation gains considerably more relevance, as we might detect something that bears no resemblance to a conventional extraterrestrial broadcast. It might present as a comet with unusual chemical properties, or an infrared source exhibiting peculiar spectral characteristics, or an object possessing polarization, attributes that defy conventional explanation. At such a juncture, the question arises: should we categorize it as natural until proven artificial, or treat it as potentially artificial and proceed with extreme caution? The protocol adopts the latter stance. It posits that any detection across any wavelength that cannot be immediately elucidated by natural phenomena should be regarded with seriousness and subjected to a rigorous process of verification and consultation. This represents a conservative methodology, prioritizing prudence. It also means that ambiguous findings, such as those associated with 3I Atlas and its collection of anomalies, fall under the purview of the protocol. They necessitate adherence to the established framework, require consultation, and may even invoke the no-reply clause, even in the absence of absolute certainty regarding their origin. The proliferation of detection instruments enhances our observational range, but simultaneously increases ambiguity. We are capable of observing and measuring more, yet we cannot always interpret these findings with complete clarity. When the implications are as profound as potentially discovering evidence of extraterrestrial technology, ambiguity becomes perilous. It is the fertile ground for conjecture, the catalyst for divergent interpretations, and the erosion of trust. The protocol's function is to manage this ambiguity, to establish a structured pathway for navigating uncertainty. Its success hinges on public confidence in the process. As we have already observed, this confidence is far from universal. Therefore, the question has evolved beyond, did we receive a signal, to, did we observe or detect anything that might be artificial? This is a considerably more complex inquiry, as the cosmos is replete with natural peculiarities. Distinguishing between natural strangeness and artificial strangeness may well be the most critical discernment humanity will ever undertake. The necessary instruments and the governing framework exist. Now we can only hope that our observations are directed at the appropriate subjects, employing the correct methodologies, at the opportune moments, and that when a discovery is made, we possess the wisdom to act appropriately. Part 7. Diplomatic and Defense Implications. An examination of how United Nations consultation might unfold. Let us consider the events following a confirmed detection. Suppose an anomaly has been verified. Multiple observatories have corroborated the finding. The observational data has been duly archived. The anomalies cannot be attributed to any known natural processes. There is a 95% certainty that we are observing a technosignature, perhaps even direct evidence of extraterrestrial technology. What transpires next? This is the point at which the protocol's legal and diplomatic mechanisms are activated, and where complexities emerge. The protocol stipulates, "No reply shall be dispatched pending appropriate international consultations." This phrase, appropriate international consultations, carries substantial weight. It is sufficiently open-ended to allow for adaptability, yet specific enough to imply a defined procedure. Let us dissect what this procedure might entail, who would be involved, and the potential pitfalls. Initially, the institutions. The International Academy of Astronautics, IAA, is the scientific body that promulgated the protocol. It is not a governmental entity, nor an international treaty organization, but rather an independent assembly of experts globally recognized for their contributions to space science and policy. In the event of a detection, the IAA would convene its post-detection subcommittee, comprising the multidisciplinary team previously discussed. This subcommittee would meticulously review the data, evaluate the credibility of the detection, and formulate recommendations regarding subsequent actions. However, the IAA possesses no enforcement authority. It cannot compel nations to act, nor can it prevent an unauthorized party from transmitting a response. Its influence lies in its capacity to confer legitimacy. If the IAA subcommittee deems a detection credible and warranting international deliberation, this carries significant influence. Governments, media outlets, and the scientific community take notice. The IAA emerges as the authoritative voice in the discourse, at least in the initial stages. The subsequent step involves the United Nations, specifically the Committee on the Peaceful Uses of Outer Space, colloquially known as COPUOS. This is the UN entity responsible for international space law and policy, the venue where treaties such as the Outer Space Treaty of 1967 were negotiated, and where issues like space debris, satellite collisions, and planetary protection are addressed. It is therefore the logical forum for discussing humanity's collective response to a confirmed extraterrestrial detection. COPUOS operates on the principle of consensus. This implies that every member state must assent before any formal resolution or recommendation can be adopted. This process is inherently slow and cumbersome, and intentionally so. The UN does not act precipitously. However, in this context, such deliberation might be a strength rather than a weakness, given that the decision to respond to an extraterrestrial intelligence, or to refrain from doing so, is arguably the most momentous choice humanity has ever confronted. Hasty decisions are ill-advised. Yet here lies a complication. What if consensus cannot be achieved? What if certain nations advocate for a response while others oppose it? What if the debate extends for months or years, during which the signal dissipates or the object moves beyond our observational range? The protocol does not provide answers to these questions. It presumes that consultation will occur, but does not specify the course of action should consultation falter. Furthermore, the International Telecommunication Union, ITU, plays a role as it regulates global radio frequencies and telecommunications. If a reply involves broadcasting a radio signal, the ITU's involvement would be necessary to ensure that the transmission does not interfere with existing terrestrial communications or contravene international frequency allocations. This introduces an additional layer of coordination and another potential bottleneck. Let us outline the procedural pathway. A detection occurs, followed by verification, the convening of the IAA subcommittee, their review of the data, and subsequent recommendation for consultation. This recommendation is then presented to COPUOS. COPUOS engages in deliberation, member states voice their opinions, experts provide testimony, committees are established, reports are drafted, and months may elapse. Ultimately, a consensus might emerge, leading to a decision to reply, to withhold a reply, or to postpone the decision pending further information. If the decision is to reply, then the task of formulating the message arises. Who undertakes this responsibility? A panel of linguists, scientists, philosophers, a single nation, or the United Nations itself? And what would the message convey? Would we introduce ourselves? Would we share information about our civilization? Would we pose inquiries? Or would we offer no substantive content, merely acknowledging receipt of the signal? These are not insignificant considerations. Every word, every symbol, carries potential ramifications. And once a message is transmitted, it cannot be retracted. However, a scenario that causes considerable apprehension is this. What if a private individual or organization detects a signal and decides to respond without awaiting consultation? The protocol mandates that they notify authorities and refrain from replying. But it lacks enforcement capabilities. There is no global SETI police force, no international legal framework with the authority to prevent someone from directing a transmitter skyward and initiating a broadcast. A Silicon Valley billionaire might decide that humanity's pace is too slow and take matters into their own hands. A government, acting covertly, might opt to send a reply as part of a classified national security initiative. A renegade scientist, frustrated with bureaucratic delays, might choose to transmit independently. The protocol anticipates these eventualities but lacks mechanisms to prevent them, representing a significant deficiency. There is also the issue of secrecy versus transparency. The protocol emphasizes open data access and public notification once a detection has been verified. However, what if a detection is classified for national security reasons? What if a government decides that information pertaining to the signal or object is too sensitive for public disclosure? The protocol holds no sway over national security classifications. If a state chooses to maintain secrecy, it can do so, thereby establishing a bifurcated system. Public science, operating under the protocol's guidelines, and classified operations, functioning without such constraints, or at least without known constraints. Historical precedents offer valuable insights. The Outer Space Treaty of 1967 established fundamental principles for space exploration, including the notion that space is the common heritage of all humankind and that nations cannot assert sovereignty over celestial bodies. This treaty has proven remarkably successful, having endured for nearly 60 years. Its success, however, stems from its addressing issues where consensus was relatively easy to achieve. In 1967, no one resided on the moon, and no immediate economic interests were at stake. The treaty could afford to be aspirational. However, a response to extraterrestrial intelligence is a different matter entirely. The stakes are existential. The implications are incalculable, and achieving consensus may prove impossible. Some nations might perceive contact as an opportunity, while others might view it as a threat. Some may desire engagement, while others may prefer to remain hidden. These disagreements are not theoretical. They are rooted in cultural and political differences, informed by divergent worldviews regarding humanity's place in the cosmos. Therefore, what does this portend for Three-Eye Atlas? If the object's anomalies cannot be attributed to natural phenomena, and if evidence mounts suggesting its artificial nature, then the protocol is activated. The detection is verified, the IAA subcommittee convenes, and consultation commences. At this juncture, the world watches. Not merely scientists and governments, but everyone. Because the question of whether to respond or how to respond becomes a global referendum on our collective identity as a species. Shall we speak with a unified voice or with many? Shall we place our trust in the institutions we have established, or shall we circumvent them? Shall we proceed with caution, or shall we venture boldly into the unknown? The protocol endeavors to provide a framework for answering these questions. However, frameworks are only as robust as the trust that underpins them. Should that trust erode, should individuals perceive the process as compromised or the consultation as a charade, the protocol would become irrelevant. A response would likely be forthcoming regardless, and we would then ascertain whether the universe is concerned with our internal political dynamics. The phrase UN consultation may sound bureaucratic and mundane, but it potentially serves as the gatekeeper for who speaks or remains silent in our initial encounter. It represents the pivotal juncture between scientific discovery and global decision-making. Its efficacy rests upon questions that remain unanswered, questions pertaining to trust, legitimacy, and humanity's capacity for collective action when the stakes are this elevated. The framework exists. The process is delineated. Now we must await the outcome. Will it be adhered to, or will someone presume to possess superior judgment? Part 8. Defense, Signals Intelligence, and Dual-Use Concerns. There exists an uncomfortable intersection between space science and national security that largely goes unrecognized. However, to comprehend the significance of the protocol and the possibility that its timing is not mere coincidence, this intersection must be understood. The detection of technosignatures is not solely a scientific pursuit. It is also potentially a matter of intelligence and defense. And when these two domains converge, the situation rapidly becomes complex. Let us begin with historical context. Early radar astronomy originated from military technology. The same radar systems designed for tracking incoming missiles and enemy aircraft were adapted for bouncing signals off the moon and nearby planets. The initial radio telescopes often served dual purposes, catering to both scientific research and defense functions. Even today, some of the world's most powerful radio dishes are operated by, or in collaboration with, defense departments. The distinction between civilian science and military intelligence has historically been blurred in the realm of space research. Now let us apply this to SETI and the detection of technosignatures. If one is searching for artificial signals emanating from space, one employs methodologies and instruments fundamentally analogous to signals intelligence. This involves scanning frequencies, identifying patterns, and distinguishing intentional transmissions from ambient noise. This is not merely astronomy. It is signals intelligence, and intelligence agencies have a vested interest in it. A laser emission could represent extraterrestrial communication, or it could be a directed energy weapon test conducted by a rival power. The infrared signature of a megastructure might signify alien engineering, or it could be a classified military installation exhibiting unusual thermal characteristics. An anomalous particle emission from an interstellar object could be attributed to exotic natural chemistry, or it could be the propulsion exhaust from a probe, either ours or theirs, which an entity wishes to conceal. The technologies we utilize for alien detection are the same ones employed for mutual surveillance, giving rise to dual-use challenges that the protocol does not fully address. Consider this scenario. A private SETI organization makes a detection. They adhere to the protocol, notifying the IAA. The IAA reviews the data and confirms its anomalous nature. However, before the IAA can issue a public announcement, a government intervenes, citing national security. The data is classified, the detection is removed from public discourse, and the researchers are instructed to maintain silence. Officially, nothing has transpired. Unofficially, intelligence analysts are scrutinizing the data for potential tactical implications. Is this paranoia? Perhaps, but it is not implausible. Governments routinely classify information, particularly that which may possess military or strategic value. A confirmed extraterrestrial detection unequivocally holds strategic importance. It alters the threat landscape, challenges assumptions about technological capabilities, and reshapes geopolitical calculations. If one nation possesses access to this information while others do not, it constitutes an intelligence advantage, and nations are reluctant to relinquish such advantages. There is also the dimension of jamming and disinformation. Suppose a detection is publicized and the data is released. Independent researchers begin their analyses. However, conflicting claims subsequently emerge. Some analysts assert the signal is artificial, while others contend it originates from a known pulsar. Still others suggest it is terrestrial interference, perhaps from a satellite or a classified military transmission. The signal becomes a subject of dispute, leaving observers uncertain. And who benefits from such confusion? A government seeking to prevent the confirmation of a detection might find muddying the waters a viable strategy. It is not necessary to prove the absence of aliens. It is sufficient to sow enough doubt to fracture consensus. This can be achieved by disseminating competing analyses, funding studies that support natural explanations, or leaking information suggesting an error by the original researchers. Complete control of the narrative is not required. The objective is simply to prevent anyone else from establishing it. The protocol's no-reply clause could be interpreted as an authorization for such tactics. If no official response is permitted until consultation is concluded, and such consultation can span months or years, then during this interim period, the information environment remains fluid and susceptible to manipulation and control. The public may never receive a clear understanding of the detected phenomenon or its implications. Now let us address the private sector. Technology corporations and space startups are increasingly involved in space activities. They launch satellites, operate ground stations, and have access to data streams and observational capabilities that rival or surpass those of traditional scientific institutions. What occurs if one of these companies makes a detection? Do they follow the protocol, or do they opt for immediate public disclosure? Perhaps publicity is perceived as a driver of stock value or an attractor of investment. Corporate incentives do not always align with scientific norms or international governance. A startup might view a detection as a branding opportunity. A tech giant might see it as a chance to position itself as a leader in extraterrestrial communication. And if they choose to broadcast a reply without authorization, what recourse is available? Legal action? Sanctions? The protocol lacks enforcement mechanisms for private entities, particularly those possessing significant resources and legal expertise. Let us return to 3i Atlas. If its unusual traits are identified as potentially artificial, how do the defense and intelligence sectors react? Do they keep tabs on the phenomenon? Do they direct satellites and ground-based instruments to maintain continuous surveillance? Are the discoveries classified? We lack definitive answers because such activities are not publicized. However, it's logical to presume that if an object from beyond our solar system exhibits peculiar behavior, someone in an interior office is paying extremely close attention. And should they uncover something significant, something that classified analysis reveals but the public is not informed of, then the established procedure becomes a convenient pretext for concealment. We are in consultation. We are verifying. We are awaiting an international consensus. Meanwhile, the true decision-making unfolds behind closed doors in classified sessions among individuals who are not required to publicly justify their assessments. The protocol frames this secrecy as scientific prudence, yet it could just as easily serve as a means of strategic control. Here lies the unsettling inquiry. If national security becomes a factor, where do we draw the line between caution and control? When does prudent consideration morph into suppression? When does oversight transform into obstruction? The protocol offers no solution to this. It is incapable of doing so, as it is an advisory document authored by scientists. And it is governments, not scientists, who hold sway over classified information. Therefore, we are left with a framework that functions effectively when all parties adhere to its stipulations, but falters the moment an entity decides those stipulations no longer apply. And in a realm where national security, commercial rivalry, and geopolitical advantage are at stake, the belief that everyone will comply is, at best, overly optimistic. The protocol attempts to mitigate this through transparency, open data, independent validation, and multidisciplinary review. The underlying principle is that widespread public access to information makes it more challenging to suppress or distort. However, transparency has its limitations. It does not extend to covert programs. It does not restrain private entities unbound by scientific principles, nor does it prevent the dissemination of misleading information designed to foster confusion rather than clarity. Here's the concluding point. If the protocol's no-reply stipulation is activated, a period, possibly protracted, emerges where only insiders are privy to developments. The public perceives ongoing consultations, but insiders witness data analysis, strategic evaluations, and contingency planning. During this interval, decisions are made, decisions concerning what information to disseminate, to whom, and how to frame it. These are decisions that shape the public perception before most individuals are even aware that a narrative is being constructed. The governance of potential extraterrestrial contact is far from an abstract academic debate. It resides at the nexus of science, intelligence, and power. And when these three elements converge, the peril extends beyond potentially misinterpreting the science. The risk lies in the science being accurate, yet the response being dictated by interests wholly unrelated to truth or openness. The protocol presents itself as a mechanism for caution, but it could equally function as a mechanism for concealment, and discerning between the two from an external vantage point may prove impossible. Part 10 delves into the anomalies dossier of 3I Atlas, focusing on its chemistry, physics, and peculiar behavior. Let us examine the specific details that render 3I Atlas so extraordinary, captivating both scientific minds and conspiracy theorists. Because the object does not conform to the expected behavior of a typical comet, the data acquired by our most sophisticated instruments is replete with anomalies, observations that deviate from established norms. While an anomaly does not inherently signify artificiality, it does indicate that we are confronting something we do not fully comprehend. Therefore, let us meticulously review the dossier, point by point, to ascertain what we are truly observing. Firstly, the chemistry. The James Webb Space Telescope has been observing 3 Atlas since late July of the year 2025, capturing spectral data of the gases emanating from the object's surface. Their findings are unusual. The coma, the diffuse cloud of gas and dust enveloping the nucleus, is predominantly composed of carbon dioxide. While this is not entirely unprecedented in comets, the ratio is exceptionally high. The proportion of carbon dioxide to water is approximately 8:1, with a margin of error of plus or minus 1. This implies that for every molecule of water released, there are 8 molecules of carbon dioxide. The vast majority of comets exhibit the inverse pattern, with water as the primary volatile substance and carbon dioxide as a secondary component. 3 Atlas entirely inverts this established relationship. Why is this detail significant? Because a comet's composition offers insights into its origin and formation environment. Comets are essentially frozen relics, preserving the chemical conditions of the primordial molecular cloud from which they coalesced. The comets within our solar system originated in a region characterized by abundant water ice, along with lesser quantities of carbon dioxide, methane, ammonia, and other volatile compounds. However, 3 Atlas originates from a different location, a distinct star system, and a separate molecular cloud. Apparently, this cloud possessed a markedly different chemical makeup, high in carbon dioxide and low in water. This scenario is plausible, as molecular clouds exhibit considerable variation. Nevertheless, this is the inaugural instance of such a signature being detected in an interstellar object, and it prompts inquiries into the specific environmental conditions that could engender such a chemical profile. Next, the polarimetry. Ground-based observatories have been measuring the degree to which light is polarized as it scatters off 3I Atlas, and the results are unprecedented. The object displays a profound degree of polarization, meaning the way light's polarization changes after scattering is unusual. The inversion angle, the point at which the polarization shifts sign, is approximately 17 degrees. This is a characteristic that astronomers have not observed in any previously catalogued comet. Polarization provides information about the physical properties of the particles responsible for scattering light, including their size, shape, and composition. All these factors influence how light interacts with dust grains and gas molecules. Conventional comets exhibit polarization patterns that align with models based on irregular silicate particles intermingled with organic compounds. However, 3 Atlas does not conform to these models. Its polarization suggests that the particles within its coma possess attributes that are novel to our understanding. Perhaps they exhibit a different size distribution, a dissimilar composition, or are structured in ways atypical for natural dust grains. We are uncertain, but the situation is indeed peculiar. Then there are the claims of metallic emissions. This is where speculation arises, as the supporting data is less robust. Some reports, predominantly from less reputable sources citing preliminary spectroscopic analyses, indicate that 3I Atlas is emitting metallic compounds, specifically nickel alloys, at a rate of approximately 4 grams per second, devoid of detectable iron. If substantiated, this would be an extraordinary phenomenon, as naturally occurring comets do not emit refined metals. While they may contain trace metals within their dust, they do not do so in the form of alloys, nor at such elevated emission rates. However, caution is warranted here. These assertions have not undergone peer review. They have not been corroborated by independent observational facilities. They are based on spectral lines that could be subject to multiple interpretations. Spectroscopy is a complex field. It involves analyzing light that has been absorbed or emitted by atoms and molecules to identify them. But spectral lines can overlap. Instruments can produce artifacts, and without rigorous analysis, misidentification of features is a distinct possibility. Consequently, the metallic emissions, while intriguing, remain unverified. They represent a data point that necessitates further investigation, rather than a definitive conclusion. Should subsequent observations confirm the presence of nickel alloys, then a significant challenge would emerge, as such a finding would be exceedingly difficult to explain through natural processes. But until such confirmation is obtained, we must regard it as a possibility, not a certainty. Now let us address its behavior. In its initial observations, 3 Atlas did not display a typical cometary tail. Comets develop tails as they approach the Sun, due to solar radiation warming their surfaces, causing volatile substances to sublimate and carry dust particles away from the nucleus. The pressure exerted by sunlight and the solar wind then propels this material into a tail that extends away from the Sun. This is one of the most recognizable features of comets. However, 3 Atlas was initially quiescent, exhibiting no prominent tail, only a faint coma. This is unusual for an object nearing perihelion, but not entirely impossible. Perhaps the surface had not yet reached sufficient temperature, or the volatile materials were shielded by a layer of refractory substances. But then, in late August, the KEK Observatory detected an anti-tail, a phenomenon that appears to point toward the Sun rather than away from it. Anti-tails are optical illusions. They occur when larger, denser particles are ejected from the comet and trail behind in its orbital path. From our perspective, these particles can seem to form a tail pointing in the opposite direction. This is rare, but it does happen. The most notable instance was Comet Halley in 1957, which exhibited a prominent anti-tail. Thus, the presence of such a feature in itself does not constitute evidence of anything extraordinary. However, when considered in conjunction with all other observations, the initial subdued activity followed by the sudden emergence of an anti-tail contributes to the perception that this object is unpredictable. So, let us step back and pose the fundamental question: can all these anomalies be attributed to natural phenomena? Yes, unequivocally. Interstellar objects originate from environments that we have not directly sampled. Their chemical compositions could be exotic, yet entirely natural. Their dust characteristics could reflect formation conditions, dissimilar to those encountered within our own solar system. The metallic emissions, if indeed real, could be a consequence of surface chemistry previously unobserved. The behavioral peculiarities might stem from an atypical rotational state or an unusual internal structure. Natural explanations are conceivable for every single data point. However, here lies the dilemma. When one anomaly is compounded by another, and every measurement yields unexpected results, at some juncture, we must inquire, is this merely an exceptionally peculiar comet, or is it something more? And this is the very question that scientists are currently grappling with. The speculative framing proceeds as follows. What if 3I Atlas is an exploratory probe, an artificial construct dispatched from another civilization to investigate distant star systems? What would such an entity resemble? Well, at first glance, it might appear like a comet. It might possess a protective outer layer of ice and dust to shield it from interstellar radiation. However, upon closer examination and scrutiny, it might reveal characteristics that do not quite align. Its chemistry could be too specific, its materials could be ones not found naturally, and its behavior might suggest deliberate action rather than random chance. We engineer our own spacecraft to withstand harsh environments. We employ ablative heat shields. We coat surfaces with protective substances. We calculate trajectories for optimal efficiency. If another civilization were to undertake a similar endeavor, their probe might not announce its presence. It might blend in until it reached its destination, and only then, if at all, would it reveal its true nature. Currently, the majority of scientists who have examined the data still favor natural explanations. The prevailing sentiment, if one exists, is that 3 Atlas is a comet. Unusual, certainly, but ultimately explainable by processes we understand or will understand with further data. And this is a reasonable stance. Extraordinary claims necessitate extraordinary evidence, and we have not yet reached that threshold. The data is suggestive, but not conclusive. However, the anomalies elevate the stakes. If the object is genuinely anomalous, if further observations confirm that it defies all natural models, then the timing of the protocol becomes more than mere coincidence. For this is precisely the scenario for which the protocol was devised. An object that might be artificial, ambiguous data, global attention, and the imperative for consultation before any rash actions are taken. Whether 3 Atlas is natural or not, it is already serving as a trial run, a test of our instruments, a test of our analytical capabilities, a test of our governance frameworks, and perhaps, depending on one's perspective, a test of our readiness for contact. Because if this object is merely the prelude, if more are to follow, then the decisions we make now will establish the precedent for all subsequent events. And we will only have one opportunity to ensure these decisions are correct. Part 10. Conspiracy Cartography. Who stands to benefit from secrecy? Let's delineate the landscape. We have a revised protocol incorporating a no-reply clause. We have an interstellar object exhibiting unexplained anomalies. We have global attention coupled with conflicting narratives. And underlying it all is a persistent question. Who benefits if this story remains undisclosed? Because that is the foundation upon which conspiracy theories are built. Not on evidence, but on motive. And to comprehend why these theories gain traction, one must understand the motivations attributed to various actors in this scenario. Let us commence with the stakeholders. Firstly, the scientific community, specifically the International Academy of Astronautics and SETI researchers. What do they gain from the protocol and from the way the 3 Atlas narrative is being presented? Credibility, for one, if they manage a potential detection responsibly. If they adhere to rigorous procedures and avoid premature pronouncements, their reputation is enhanced. Funding is another aspect. High-profile detections, even ambiguous ones, pique public interest, which in turn attracts funding. Consequently, scientists have a vested interest in exercising caution, adhering to the protocol, and avoiding the embarrassment of claiming extraterrestrial contact when it turns out to be merely a comet. However, they also possess an incentive to make discoveries. Careers are forged through groundbreaking achievements, and Nobel Prizes are awarded for paradigm shifts. Thus, a tension exists. Be cautious, but not so excessively cautious as to overlook something truly extraordinary. This inherent tension creates a space for divergence of opinion within the scientific community. And these disagreements can be exploited by individuals seeking to find flaws in the official account. Next, the United Nations and space governance bodies such as UN CUPUOS. What do they gain? Authority. If the protocol is observed and consultations proceed through official channels, then the UN becomes the central hub for the most significant conversation humanity has ever engaged in. This represents soft power on an unprecedented scale. It validates the UN's role in space governance at a time when that role is being challenged by private corporations and nationalistic space initiatives. Therefore, the UN has a vested interest in ensuring the protocol is followed, ensuring that any detection or response is routed through them. However, they also have an incentive to prevent chaos. If a detection occurs and the public panics, if markets collapse, or if social order disintegrates, that constitutes a failure of governance. Consequently, the UN might prefer to manage information judiciously, releasing details incrementally, and framing the narrative in a manner that minimizes disruption. And this preference for stability could easily be perceived as suppression by those inclined to view it that way. Now, nation-states, governments, possess intricate and occasionally conflicting interests. Security and control are obvious priorities. If a detection carries strategic implications, if it alters the threat landscape or unveils novel technologies, governments will seek to control that information. They will not want adversaries to possess it. They will not want the public to panic. They will not want to relinquish the advantage conferred by possessing knowledge that others lack. However, governments must also navigate domestic politics. If citizens believe their government is withholding information regarding extraterrestrial contact, trust erodes and legitimacy diminishes. Thus, a delicate balance must be struck. Control the information, but avoid appearing to exert such stringent control that public dissent arises. This is a challenging tightrope to walk, and different governments will traverse it in varying ways, influenced by their political cultures and institutional structures. Private observers and citizen scientists have entirely different motivations. They stand to gain independence, credibility, and an audience. If a private group makes a detection and publicizes it, they achieve renown. They bypass traditional gatekeepers. They demonstrate that government grants or university affiliations are not prerequisites for contributing to humanity's most profound questions. Therefore, private entities have an incentive to go public swiftly, to circumvent the protocol, and to claim credit before any directive to remain silent can be issued. However, they also face risks. If they are mistaken, If their detection proves to be a false positive, their credibility will be irrevocably damaged. Consequently, even private actors have reasons to exercise caution, to verify their findings, and to adhere to at least some of the protocol's procedures, even if not strictly obligated to do so. Then there are the alternative media outlets and live streamers. Their motivations are straightforward: audience engagement and click-through rates. Conspiracy theories generate viewership. Drama fosters engagement. If the narrative is about scientists proceeding with caution and following established procedures, it is uninteresting. However, if the narrative is about governments concealing evidence of extraterrestrial life, that is compelling. It is shareable. It goes viral. Thus, alternative media outlets have an incentive to interpret every ambiguity as evidence of a cover-up, and every delay as proof of suppression. Now let us formulate some hypotheses. Hypothesis 1: honest precaution. The authorities, both scientific and governmental, genuinely desire to avert premature sensationalism or public alarm. They are aware of past instances of false alarms. They recognize the repercussions of erroneous pronouncements. Therefore, they are adhering to established procedures, exercising caution, and awaiting further data before making any definitive claims. Under this hypothesis, the protocol is precisely what it purports to be: a framework for responsible governance. Hypothesis 2: bureaucratic entrenchment. The protocol is being utilized by governments and international bodies to maintain centralized decision-making. This is not due to a specific secret being guarded, but rather because institutions inherently favor control. They prefer to manage narratives, coordinate responses, and ensure that no rogue entity disrupts the established process. Under this hypothesis, the protocol serves institutional interests more than public ones, but without any grand conspiracy, merely bureaucracy functioning as bureaucracy typically does. Hypothesis 3: a staged trial. Both the protocol and 3 Atlas are integral components of a preparatory exercise. Authorities are aware or suspect that contact is imminent, perhaps not from this specific object, but soon, and they are employing this event to test systems, to observe information flow, public reaction, and the behavior of various actors. Under this hypothesis, 3 Atlas is significant, but its importance lies in what it reveals about our preparedness, rather than necessarily about the object itself. The protocol is not a reactive measure. It is a preparatory one. Hypothesis 4: genuine concealment. Something has been discovered regarding 3 Atlas, or something was discovered previously that is being withheld from the public. Perhaps the object's anomalies are more profound than what has been reported. Perhaps communication has been received, a signal, something that unequivocally identifies it as artificial. Possibly, classified observations have revealed characteristics that defy natural explanation, and the protocol's consultation phase is, in reality, a guise for clandestine deliberations regarding the appropriate course of action. Under this hypothesis, the public narrative is sanitized. The actual story remains classified. Now let us evaluate these hypotheses against the available evidence concerning honest precaution. The evidence includes the documented timeline of the protocol's revision, the public accessibility of data, the involvement of multiple independent observatories, and the absence of leaked information suggesting a cover-up. Scientists appear to be acting as they state they are, observing, analyzing, and debating. This aligns with standard scientific practice, countering the notion of honest precaution is the timing. The protocol is introduced concurrently with the arrival of 3 Atlas. The no-reply clause emerges precisely when it might be most needed. This is either remarkable foresight or an extraordinary coincidence, and coincidences tend to breed suspicion. Regarding bureaucratic entrenchment, the evidence lies within the structure of the protocol itself, which consolidates authority within bodies such as the IAA and UN COPUOS. The protocol explicitly prohibits individual or organizational responses without prior consultation. This is formalized control, and institutions have a long-standing inclination towards control over chaos. Even when personal inclinations favor them over the general welfare, transparency serves as a bulwark against undue influence from bureaucratic factions. The operational framework is accessible to the public. Research findings from the 3I Atlas project are being disseminated through scholarly publications. Live broadcasts meticulously examine every aspect. If this were merely a matter of bureaucratic obstruction, one would anticipate a reduction in accessible information, not an increase, suppression rather than disclosure. The very fact that we are engaged in this discussion implies that the barriers are more permeable than impenetrable. Regarding the hypothesis of a staged test scenario, the supporting evidence is indirect. The emphasis within the operational framework on established procedures, synchronized efforts, and management of communication does indeed resemble a preparatory exercise. When anticipating future engagement scenarios, it is prudent to test one's systems using a realistic yet manageable situation. The 3 Atlas project fits this description perfectly. It presents a scenario sufficiently unusual to warrant attention, yet not so extraordinary as to necessitate immediate and decisive action. Its ambiguity allows for observation of how different participants interpret and react to uncertainty, whereas the primary weakness of the stage test hypothesis is the absence of direct corroboration. We possess no official documents indicating that 3 Atlas is being utilized as a trial case, nor have any internal informants come forward to confirm this. It is a theory that aligns with the observable facts, but other theories do as well, and without further substantiation, it remains purely speculative. True secrecy is evidenced by the lack of any disclosure. We are not privy to classified observations, nor are we aware of the activities undertaken by defense and intelligence agencies behind closed doors. Our access to the complete data set is limited to what has been publicly revealed. Should something truly exceptional have been discovered and subsequently classified, we would be entirely unaware. By its very definition, successful clandestine operations remain unseen. However, the challenge of maintaining genuine secrecy is considerable. Contemporary astronomy operates on a global scale, with observatories situated across various continents and data shared extensively. Concealing something genuinely remarkable would necessitate the coordinated efforts of dozens, if not hundreds, of organizations and thousands of individuals spanning multiple nations. This presents a significant logistical hurdle. Leaks are inevitable, and whistleblowers frequently emerge. The greater the magnitude of the secret, the more difficult it becomes to contain. To date, there have been no credible leaks suggesting that 3 Atlas is anything other than what has been publicly reported. This leaves us in a state of uncertainty. Each proposed explanation is supported by some evidence, yet each also has its deficiencies. This ambiguity provides fertile ground for conjecture. as individuals tend to fill knowledge gaps with narratives that align with their pre-existing beliefs when the truth is unclear. Those who place their trust in established institutions are more inclined to view the situation as prudent caution, while those who harbor skepticism towards authority may lean towards theories of bureaucratic control or genuine concealment. Individuals who perceive a pivotal moment in history might favor the stage test hypothesis. Your personal interpretation reveals as much about your own perspective as it does about the facts themselves. Now let us examine who stands to gain from secrecy, as this is fundamental to understanding conspiracy theories. If a cover-up is indeed in effect, who benefits? Governments could gain valuable time to prepare, strategize, and position themselves favorably. They could exert control over the prevailing narrative, thereby influencing public reactions. This could help them avoid widespread panic, societal disruption, or economic instability, at least in the immediate future. Nevertheless, they also risk forfeiting their credibility if the truth eventually surfaces, and the public realizes they have been deceived. Private entities might profit if contact or discovery leads to advancements in technology, the emergence of new markets, or unforeseen opportunities. If a corporation secures access to extraterrestrial data or artifacts before its competitors, it would confer a substantial competitive advantage. Consequently, corporate players might have a vested interest in suppressing information that could equalize the competitive landscape or invite regulatory scrutiny. The alternative media sector could experience an increase in readership and influence by portraying itself as a source of truth against official falsehoods. Every instance of delay, every ambiguous statement, every unanswered question can be interpreted as evidence of a conspiracy within their narrative framework. Such narratives resonate with individuals who already distrust established institutions, creating a self-perpetuating cycle. However, consider the opposing perspective. Who benefits from openness? Scientists gain from transparency, as open access to data facilitates more robust scientific inquiry, fosters collaboration, and accelerates progress. The general public benefits as well. Access to information empowers informed decision-making, alleviates anxieties about the unknown, and cultivates trust in institutions. Humanity as a whole would benefit, because responding effectively to potential extraterrestrial contact necessitates broad public agreement and consensus. Such consensus cannot be built upon a foundation of secrecy. Therefore, the conflict lies not merely between secrecy and transparency, but between short-term advantages and long-term interests. While secrecy might serve specific, narrow interests in the short term, transparency represents the only viable path to sustainability in the long run. The critical question is whether the involved parties recognize this reality, or if they are prioritizing their immediate needs at the expense of future well-being. Allow me to illustrate this with a game theory scenario. Imagine two participants, the public and the state. The state possesses information, while the public desires it. The state has the option to either share or withhold this information. The public, in turn, can choose to either trust or distrust the state's actions. If the state shares the information and the public trusts this disclosure, all parties benefit. Information flows freely, collective decisions are made, and institutional legitimacy is upheld. Conversely, if the state withholds information and the public maintains its trust, the state achieves short-term control, but risks long-term exposure. and a loss of credibility. Should the state share information, but the public distrusts it? The result is chaos due to misinterpretation or rejection of the data. The most unfavorable outcome occurs when the state withholds information and the public distrusts it, leading to a complete breakdown of information exchange, trust, and cooperation. Currently, our situation falls somewhere between these extremes. The state, broadly encompassing scientific and governmental bodies, is releasing some information, though not necessarily all of it. The public, similarly broadly defined, is divided, with some exhibiting trust and others exhibiting distrust, a division that fuels divergent narratives. The protocol endeavors to manage this dynamic by establishing a structured process. However, structure is only effective if it is accepted, and acceptance hinges on trust. This brings us back to the fundamental challenge. Trust is fragile, and once eroded, it is exceptionally difficult to reconstruct. So, who benefits from secrecy? In the immediate context, those who hold power and wish to retain it. In the long term, however, no one benefits. The eventual revelation of secrets often triggers public backlash, and such backlash can dismantle the very institutions that attempted to keep them hidden. The sole uncertainty lies in whether we are still within the initial phase, or approaching the point where the long-term consequences become unavoidable. Here is a concluding thought. Speculation flourishes because numerous questions remain unanswered. Our understanding of 3 Atlas is incomplete. We are unaware of discussions that have transpired in private meetings. We do not know which observations are classified. We are uncertain about the decisions that have been made regarding how to respond if the object proves to be extraordinary. In the absence of definitive answers, individuals construct their own explanations. Some of these interpretations represent reasonable extrapolations, while others are fueled by paranoid fantasies, and the majority fall somewhere in between. The existence of a motive does not equate to proof. The fact that someone might benefit from secrecy does not confirm that secrecy is occurring. The suspicion that the timing is coincidental does not imply deliberate orchestration. The inherent power of institutions does not automatically indicate their misuse, nor does it preclude it. However, that ambiguity, that void between our known facts and our suspicions, is where conspiracy theories take root, not in concrete evidence, but in the gaps of our knowledge. Until these gaps are filled, the conspiracy narrative will persist. This is because plausible justifications for secrecy exist, just as there are plausible justifications for transparency. The truth, as is often the case, likely resides somewhere in the middle, a conclusion that may be unsatisfying, but is ultimately the most probable. Part 11. JWST's Tiny Red Dots. Are we witnessing the nascent stages of black hole stars? Let us shift our focus for a moment to a subject that, at first encounter, may seem entirely unrelated to 3 Atlas, yet holds considerable significance when considering detection, oversight, and the definition of what constitutes the extraordinary. While the revision of the protocol and the interstellar object have commanded public attention, the James Webb Space Telescope has been subtly discovering celestial bodies in the deep cosmos that defy our established models, challenging our assumptions about the natural order, the realm of possibility, and our ability to differentiate between the two. The most recent enigma is what astronomers have dubbed tiny red dots. These are exceptionally compact and intensely red objects identified in JWST's infrared imagery of the early universe. They are luminous, diminutive, and their spectral characteristics suggest they may be black holes enveloped within stars, a configuration so unconventional it strains credulity. However, if these observations are validated, and these entities are indeed real, then we are observing a class of objects previously unknown to science. This has profound implications. The data reveals these objects to be incredibly dense, smaller than typical galaxies, but significantly more radiant than individual stars. Their color profile is redder than nearly anything else in the images, suggesting they are either exceptionally rich in dust, highly redshifted, or both. When astronomers analyze their spectra, they detect emission lines that do not precisely align with any recognized category. Not ordinary stars, not typical galaxies, not standard black holes, but something in between, or perhaps something entirely novel. One prevailing hypothesis posits that these are host stars for black holes, theoretical entities where a black hole resides at the core of a massive star, drawing material from the star's nucleus and emitting energy outwards. Such a configuration is expected to be unstable, short-lived, and potentially impossible. Yet, the data indicates their existence, at least within the early universe. If this holds true, it represents a fundamental expansion of our understanding of astronomical possibilities. Now, why is this relevant to 3 Atlas and its protocol? Because it alters our benchmark for what is considered anomalous. Prior to the JWST, our understanding was based on models. We had established expectations for the appearance of stars, galaxies, and black holes. When we encountered something that deviated from these models, we faced 2 choices: either revise our models or consider explanations beyond the natural realm. However, the JWST is demonstrating that the universe is more astonishing than our models had predicted, revealing natural phenomena we had not anticipated and configurations we deemed impossible. This implies that the threshold for declaring something extraordinary has been elevated. If stars harboring black holes can exist naturally, and if ultra-compact red objects are simply a new classification of astrophysical phenomena, then detecting something peculiar is insufficient grounds for concluding it is artificial. One must first eliminate all possible natural explanations, including those yet to be conceived. This is a more formidable task than it may initially appear. Consider this analogy. Imagine driving along a road and observing something in the distance that bears no resemblance to any vehicle you have ever encountered. It hovers, operates silently, and moves in ways that defy your understanding of aerodynamics. Your initial thought might be, "This is unnatural. It must be technology." However, you then learn about a novel type of drone, an experimental aircraft design, or a rare atmospheric condition that produces optical illusions. Suddenly, the bar for concluding the presence of an alien spacecraft is significantly higher, as you now have a broader range of natural explanations to rule out. The JWST is expanding our inventory of natural phenomena at a pace that outstrips our capacity to update our intuitive understanding. Each deep-field image unveils structures we did not anticipate. Each spectroscopic analysis identifies molecules in unexpected locations. Every observation challenges an assumption we believed to be firmly established. While this is immensely beneficial for scientific advancement, it complicates the framework for identifying potential extraterrestrial technology. The more we learn about what is naturally possible, the more challenging it becomes to pinpoint what is not. Now let us apply this to the search for technosignatures. The protocol emphasizes multidisciplinary review precisely because anomalies can have diverse origins. A spectral line that appears to be industrial emissions might be the result of exotic chemical reactions. A polarization signature that seems artificial could originate from a novel type of dust grain. A trajectory that suggests propulsion might be a gravitational interaction that our models did not account for. The JWST is providing evidence that the universe is replete with surprises, the majority of which are natural in origin. However, there is a flip side to this. If natural phenomena are stranger than we previously imagined, then the distinction between the artificial and the natural becomes blurred. This does not render the task impossible, but it demands more data, greater rigor, and extended observation periods. Time is a crucial resource that the protocol seeks to secure through its no-reply provision. The rationale is that if an ambiguous phenomenon is detected and an immediate response is issued, it might be directed towards a natural occurrence that has been misidentified. However, by delaying, verifying, and systematically ruling out all conceivable natural explanations, including those recently revealed by the JWST, any subsequent response becomes informed, deliberate, and less prone to error or embarrassment. Therefore, the significance of the JWST's tiny red dots lies in their powerful reminder of the vastness of our ignorance. We are still in the process of discovering fundamental categories of objects within the universe and expanding our comprehension of what is naturally feasible. This process of expansion is ongoing. We are unlikely to reach a definitive point where we possess complete knowledge and can confidently assert anything beyond this must be artificial. We will perpetually operate at the vanguard of knowledge, continually uncovering new natural phenomena that challenge our existing paradigms. This brings us to the matter of governance. If our baseline for what constitutes normalcy is continuously shifting, how do we establish rules for identifying abnormality? The protocol attempts to address this by mandating verification and consultation, but it cannot account for unforeseen circumstances or future discoveries that redefine the boundaries of the possible. Consequently, governance must be adaptable, flexible, and willing to evolve as our understanding grows. Consider a speculative scenario. Could future discoveries of tiny red dots trigger the protocol's reply-no-reply decision matrix? It is highly improbable, given their immense distance, billions of light-years away. We observe them as they were in the early universe, long before Earth existed. However, what if the JWST were to detect such an object in our vicinity? What if a compact infrared source exhibiting anomalous spectral features were discovered within our own galaxy, or even our solar system? At what juncture would such a detection transition from an interesting scientific finding to a potential technosignature? The answer depends on various factors: context, proximity, observable behavior, composition, and repeatability. All these elements contribute to the assessment. A tiny red dot, situated 13 billion light-years away, is a matter of scientific fascination, but not actionable. A similar object located 100 light-years away, exhibiting signs of modulation or directional movement, might warrant further investigation. And a comparable object passing through our solar system, displaying chemical signatures that do not correspond to any known natural source, would undoubtedly trigger a response. 3 Atlas occupies a middle ground in this spectrum. It is present, relatively close, and exhibits anomalies. However, the crucial question remains: are these anomalies significant enough to necessitate the full activation of the protocol's machinery. This depends on how robustly these anomalies withstand scrutiny, how many natural explanations can be systematically eliminated, and the level of confidence in the remaining assessments. The discoveries made by the JWST serve as a potent reminder that the process of ruling out natural explanations is continuous, not a one-time event. Thus, the essential lesson is this: as the cosmos unveils increasingly peculiar natural phenomena, the distinction between the natural and the artificial becomes increasingly indistinct. We cannot rely on intuition alone, nor can we depend on models that are perpetually being revised. Our reliance must be placed on established processes, rigorous verification, multidisciplinary consultation, and a patient approach. This is precisely what the protocol aims to enforce. Its architects are not characterized by slowness or excessive caution. Rather, they are acutely aware of the ease with which one can arrive at erroneous conclusions. History is replete with instances where the observation of something unusual led to hasty judgments that were later sources of embarrassment. Black hole stars, if they prove to be real, serve as a compelling illustration of nature exceeding the bounds of fiction. These are entities that, according to older models, should not exist, but, according to current data, apparently do. If nature can surprise us in such a manner, if the universe can manifest configurations we deemed impossible, then we must approach every anomaly with a profound sense of humility. The universe operates according to its own laws, irrespective of our expectations. Our task is to decipher its reality, not to impose our preconceived notions upon it. As our capacity for detecting the unusual expands, the imperative for robust governance frameworks intensifies. These frameworks are not intended to stifle discovery, but to manage it responsibly. They aim not to silence voices, but to ensure that our pronouncements, our acknowledgments of findings, our responses, our claims about what we have uncovered, are firmly grounded in the most current evidence and the most meticulous analysis available. The JWST is extending our observational reach. The protocol strives to ensure that this reach does not exceed our grasp. Its success hinges on our ability to harmonize curiosity with prudence, ambition with humility, and speed with rigor. Achieving this equilibrium is challenging. However, if 3 Atlas offers any discernible lesson, it is that this balance is more critical now than ever before. Part 12. A Quantum Ingenuity for Solar Energy. Unraveling a century-old quantum mystery. While astronomers have been intently observing the heavens, engineers on the ground have been actively redefining fundamental principles. One such paradigm shift pertains to solar energy, quantum mechanics, and a breakthrough that, while sounding esoteric, has significant implications for how we detect, monitor, and respond to phenomena such as 3 Atlas. This is because the narrative surrounding the detection of technosignatures is not solely confined to advanced telescopes and governmental bodies. It also encompasses questions of accessibility to the necessary tools, the financial capacity for participation, and the accelerating pace of democratization in observational capabilities. The breakthrough researchers have achieved involves what they term a century-old quantum secret, a method for substantially enhancing solar cell efficiency by leveraging quantum effects that were theoretically predicted decades ago, but only recently translated into practical devices. The technical details encompass concepts such as quantum tunneling, multi-junction cells, and hot carrier extraction. A deep understanding of the underlying physics is not essential to grasp the broader implications. Solar power is poised to become more affordable, more efficient, and more widely accessible. Why is this development significant for space observation? Because power availability represents the primary limiting factor for most sensor networks. Operating a radio telescope demands power. Deploying and maintaining a constellation of satellites requires power. Establishing a private search for extraterrestrial intelligence (SETI) station in one's own backyard necessitates power. If the cost of power generation decreases, and if greater electrical output can be achieved from smaller, lighter, and more easily deployable panels, then the barrier to entry for participation will be significantly lowered. This will enable a larger number of entities to engage, facilitate the deployment of more extensive sensor networks, and lead to the collection of a greater volume of data. Let us consider this in tangible terms. Currently, large-scale SETI initiatives are predominantly spearheaded by institutions possessing substantial financial resources, including universities, government agencies, and international consortia. They command the means to construct and operate large radio dishes, process immense quantities of data, and sustain observational campaigns that span years or even decades. However, what will occur when a private group, perhaps a nascent startup or a wealthy individual, can achieve comparable capabilities at a considerably reduced cost? What scenarios emerge when sensor networks become so inexpensive that they can be blanketed across an entire continent, thereby creating a distributed detection system beyond the control of any single institution? This is precisely where the challenges of governance become intricate. The existing protocol is predicated on a specific institutional structure. It assumes that detections will occur through established channels, that data will be processed via recognized pipelines, and that coordination will be facilitated among known actors. However, if technological advancements democratize observational capabilities, and if detection potential becomes widely dispersed, the protocol's foundational assumptions begin to falter, as coordinating with an unbounded number of entities becomes unfeasible. You cannot impose notification mandates on tens of thousands of independent entities. Furthermore, you cannot stop an individual from broadcasting a response if they possess the necessary equipment and the desire. This scenario is not a mere hypothetical. We are already witnessing the initial stages of this transition. Projects focused on public participation in scientific endeavors, such as SETI at Home, have distributed computational tasks across millions of personal computers, enabling ordinary individuals to contribute to data analysis. Similarly, privately funded satellite initiatives, like Planet Labs, have placed Earth observation capabilities into the hands of commercial enterprises. Enthusiast radio astronomers are successfully detecting celestial pulses and mapping the cosmos using apparatus they've assembled in their own workshops. The sophistication and affordability of these tools continue to improve annually. Additionally, advancements in solar power technology are diminishing the limitations previously imposed by energy constraints. This allows for the deployment of sensor networks in remote areas without reliance on established power grids. Continuous operation is feasible, eliminating concerns about fuel expenses or battery longevity. Scaling up operations no longer necessitates a proportional increase in infrastructure expenditures, representing a significant paradigm shift. Now let's connect this back to the 3I Atlas mission. Envision a private organization equipped with advanced, solar-powered sensors that utilize quantum enhancement technology. Such a group might detect an anomaly in the object's emissions, perhaps a faint radio transmission, an optical flash, or a particle signature that deviates from the official observations recorded under the established protocol. Their prescribed course of action would be to inform the International Astronomical Association, IAA, archive their findings, and await further deliberation. However, what if they choose not to follow these guidelines? What if they opt to publicly disclose their discovery immediately, or worse, initiate a response independently? The current protocol lacks any enforcement mechanism to address such a situation. It cannot confiscate their equipment, nor can it suppress their broadcasts. It is powerless to prevent them from uploading their findings to the Internet, where they would be accessible to millions within moments. Once information is disseminated and goes viral, it becomes impossible to retract. The consultation process becomes irrelevant. The narrative has already been shaped, and the world has begun to react. For some, this decentralized approach will be viewed as a positive attribute, not a flaw. This democratization signifies increased accountability. It ensures that no single entity holds a monopoly over the prevailing narrative. Transparency is inherently enforced by the sheer volume of observers, each acting as a check on the others. Should an extraordinary detection occur, the global community will become aware of it, irrespective of the wishes of governments or international organizations. Conversely, others will perceive this as a threat to a unified response. If any individual can make a detection, and any individual can respond, humanity will not present a singular voice. Instead, we will speak with millions of voices, some informed, some reckless, some well-intentioned, and some malicious. This cacophony could prove perilous because when attempting to communicate with extraterrestrial intelligence, or even merely to study an interstellar object, consistency is paramount. Clarity is essential. Achieving clarity becomes impossible when everyone is broadcasting their own distinct message. Moreover, the issue of false positives is a significant concern. Accelerated technological capabilities lead to faster detections, but they also increase the likelihood of errors. If a private operator detects something and disseminates it without rigorous validation, only for it to be revealed as a satellite glint or an equipment malfunction, the damage to credibility is already inflicted. Public trust erodes, and subsequent claims are met with suspicion. The signal-to-noise ratio within the information landscape deteriorates rather than improves. The protocol attempts to mitigate this by emphasizing validation, peer review, and corroboration from multiple observatories. However, these processes are inherently time-consuming, and time is precisely what advanced technology compresses. If a detection can be made in minutes and published in seconds, the validation procedures struggle to keep pace. The traditional model of meticulous, deliberate analysis yields to real-time information warfare, where the initial assertion dictates the narrative, irrespective of its accuracy. The broader implication here is that when technology becomes both inexpensive and pervasive, governance cannot rely on centralized control. Instead, it must depend on distributed norms, a shared understanding of best practices, and cultural expectations regarding responsibility and verification. The protocol represents a step in this direction, an endeavor to establish such norms. However, norms are only effective if individuals accept them. If people distrust the institutions promoting these norms, they will disregard them. Consequently, the quantum solar breakthrough, and all other concurrent technological advancements are accelerating a transformation that the protocol is struggling to manage. This transformation involves a shift from centralized, institutionalized observation to decentralized, democratized observation, from controlled access to open dissemination, and from slow, deliberate analysis to rapid real-time responses. While this paradigm shift offers substantial benefits, making science more inclusive, transparent, and resilient to institutional failures, it also introduces risks. It complicates coordination, decelerates verification, and amplifies the probability of errors. When dealing with matters as significant as potential extraterrestrial contact, these risks carry considerable weight. The decisions we make, the messages we transmit, and the responses we choose have implications extending far beyond our immediate concerns, impacting humanity as a whole. If these critical decisions are determined by those possessing the fastest equipment and the loudest voice, rather than through careful collective deliberation, we risk encountering outcomes that no one desires. The protocol is an attempt to navigate this inherent tension, seeking to balance speed with rigor, access with coordination, and individual liberty with collective obligation. Its success hinges on whether individuals perceive the protocol as legitimate and beneficial, as something worth adhering to even when inconvenient. Such legitimacy cannot be imposed. It must be earned through transparency, inclusivity, and demonstrable evidence that the process functions effectively and yields superior outcomes compared to alternatives. The necessary tools and the foundational framework are in place. The crucial question is whether we possess the foresight to utilize them wisely, or if technological progress will outpace our governance capabilities, leaving us struggling to manage unforeseen consequences. The 3I Atlas mission serves as a test case, and this test extends beyond the object itself. It is a test of humanity's capacity for coordination during critical junctures. It examines whether increased speed and accessibility enhance our collective strength or merely lead to greater disarray. The ultimate answer, as always, will be determined by our subsequent actions. Part 13. The James Webb Space Telescope, JWST, has identified carbon compounds within the ice clouds of the Large Magellanic Cloud, a discovery with significant implications for the detection of life. Let us now focus on the topic of life itself, not necessarily intelligent life, but life in its fundamental form. While considerable attention is directed towards technosignatures and interstellar probes, the James Webb Space Telescope has been making equally profound discoveries. It has detected the very building blocks of life preserved in icy formations within the Large Magellanic Cloud, a galactic satellite situated 160,000 light-years from Earth. These findings carry significant implications for our understanding of detection methodologies, the nature of our search, and how established protocols should address the inherent ambiguities that exist between technological and biological phenomena. The JWST's observations revealed complex carbon-based molecules within ice grains surrounding nascent stars in the Large Magellanic Cloud. These include compounds such as polycyclic aromatic hydrocarbons, which are organic molecules serving as precursors to the chemistry of life as we currently understand it. While such compounds have been previously identified within our own galaxy, in molecular clouds and planetary systems closer to home, their detection in another galaxy, within environments possessing distinct chemical characteristics, offers a crucial insight. The fundamental ingredients for life are universally present. They naturally emerge wherever conditions are conducive. This realization is critical because biosignature science, the field dedicated to searching for evidence of life, is advancing at an accelerated pace. Our investigations are now extending beyond the mere detection of gases like oxygen or methane in exoplanet atmospheres. We are actively seeking out chemical disequilibria, combinations of gases that would not naturally coexist without an active biological source. Furthermore, we are analyzing surface features that could indicate biological activity and scrutinizing patterns in light curves for potential signs of vegetation or microbial mats. The scope of what constitutes a potential biosignature is expanding, mirroring the broadening scope of technosignatures. However, this is where complexity arises. Distinguishing between biology and technology is not always straightforward. A biosignature and a technosignature can present similar characteristics. For instance, the presence of oxygen in an atmosphere could be the product of photosynthetic organisms or the result of industrial processes. A modulated radio signal might originate from a natural maser, amplified by biological processes, or it could be a deliberate transmission from a technological civilization. These distinctions become blurred, particularly at the limits of our observational capabilities, and this blurring has significant implications for governance. The protocol specifically addresses technosignatures, focusing on the detection of evidence related to technology. But what if we detect evidence of life that is not technological in nature? What if we discover biosignatures on an exoplanet, within an interstellar object, or in samples retrieved from Mars? Does the protocol still apply? Should we respond to a biosphere in the same manner we would respond to a civilization? These questions are not explicitly addressed in the current draft and require careful consideration. Let us re-examine the 3I Atlas mission through this perspective. What if the anomalies detected in the object are not technological but biological? What if the 3I Atlas is carrying prebiotic material, or even active biotic elements, from another star system, and these are responsible for the unusual chemistry we are observing, the elevated ratio of carbon dioxide, the exotic polarization signature, and even the unconfirmed metallic emissions could all potentially be explained by biological processes that are currently unknown to us. Panspermia, the hypothesis that life can disseminate between star systems via comets and asteroids, is a scientifically valid concept. If microorganisms or organic compounds possess the resilience to survive the journey through interstellar space, shielded within ice and protected from radiation, then interstellar objects, such as 3I Atlas, are plausible vectors. They could be instrumental in seeding star systems with the raw materials for life, or even with life itself. In such a scenario, detecting biosignatures within 3I Atlas would transcend mere scientific interest. It would be a paradigm-shifting discovery. Crucially, it would also reintroduce the question of response in a novel context. Would we attempt to communicate with a comet teeming with microbes? It is unlikely, as there would be no intelligent entity to engage with. However, what if the detected biosignatures are ambiguous, suggesting both biological and technological origins, and the distinction remains unclear? The protocol's consultation mechanism is designed to handle such ambiguities, but it presumes that the ambiguity pertains to whether something is natural or artificial in a technological sense. It does not fully encompass the possibility of detecting non-intelligent life. the draft protocol does acknowledge the necessity of multidisciplinary review, which would include biologists and astrobiologists, indicating at least a recognition that life detection is part of the broader picture. However, the primary emphasis remains on intelligence, communication, and the question of response. This emphasis may be too restrictive. The detection of life, even non-intelligent life, originating from beyond Earth, would constitute one of the most profound discoveries in human history. Our response, our methods of study, and our approach to preservation or interaction are questions that warrant the same level of rigorous governance as the technosignature issue. Consider the following scenario. JWST data pertaining to 3I Atlas reveals organic compounds that do not align with any known abiotic processes. The ratios of amino acids suggest a biological origin, isotopic signatures point towards metabolic fractionation, and the observed morphologies within the dust grains resemble fossilized microstructures. Individually, none of these findings are conclusive. They are all open to interpretation and debate. However, their cumulative suggestiveness makes them impossible to dismiss outright. Under the current protocol, such a detection would necessitate consultation. The IAA subcommittee would review the data, and experts in biology, chemistry, geology, and astrobiology would offer their assessments. The outcome might be an admission of uncertainty. We cannot be certain. It could be life, or it could be exotic chemistry. Further data is required. In this state of ambiguity, should we attempt communication? Should we transmit a message to 3I Atlas on the off chance that an intelligent entity is present or that something capable of interpreting a signal exists? Alternatively, should we treat it as a scientific sample, to be studied passively without any attempt at interaction? These are not straightforward questions, and they highlight the need for the protocol to evolve. The universe of potential discoveries is far broader than simple radio signals from distant civilizations. It encompasses biosignatures, chemical anomalies, physical structures, and behaviors that defy our current models. Each of these categories requires its own set of guidelines and a distinct framework for decision-making. The JWST's discovery of carbon compounds in the Large Magellanic Cloud underscores that the fundamental building blocks of life are ubiquitous. This implies that life itself may be common, even if intelligent life remains rare. Consequently, the probability of detecting life increases. We may find biosignatures on exoplanets, within our own solar system on bodies like Mars, Enceladus, or Europa, or even within interstellar objects passing through our celestial neighborhood. When these discoveries occur, we will require established rules for our response. These rules must account for the distinctions between biological and technological phenomena, and between intelligence and mere chemical processes. The protocol represents a foundational step, but it is currently incomplete. It primarily addresses scenarios involving the detection of a signal, something intentional that necessitates a reply. It is less clear on situations where something ambiguous is detected, something that might be life, but might also not be, something that challenges our existing categories and compels us to carefully reconsider our definitions of contact and response. As our capacity for detecting life expands, the question of when to speak becomes increasingly significant. Communicating with an intelligence is fundamentally different from communicating with a biosphere, and discerning which scenario we are facing is the core challenge. The protocol aims to create a space for such discernment, facilitating consultation, review, and multidisciplinary analysis. However, its effectiveness depends on our willingness to broaden our perspective beyond the conventional SETI model of a radio signal from an alien civilization, to encompass all the diverse ways life might manifest itself. This expansion is essential because the universe is unlikely to conform neatly to our preconceived categories. It will undoubtedly surprise us and present phenomena we did not anticipate. We must therefore be prepared to respond intelligently, regardless of whether what we discover is intelligent or not. Consequently, the findings from the JWST are profoundly important. They not only inform us about the locations of life's building blocks, but also serve as a crucial reminder that the detection of life is not a distant hypothetical future event. It is an ongoing reality. The 3I Atlas mission, with its array of anomalies, stands at the nexus of these critical questions. Is it technological, biological, or merely chemical in nature? We do not yet possess a definitive answer. However, the protocol operates under the assumption that we will ascertain this before making any decisions regarding a response. This assumption may prove to be overly optimistic, as the universe does not always provide clear-cut answers. Instead, it often presents us with ambiguity, compelling us to make decisions and act in the face of uncertainty, fully aware that our choices carry unpredictable consequences. Part 14. The advent of quantum computing is poised to fundamentally alter our understanding of error margins in scientific detection. A new class of machines has emerged, possessing computational capabilities far exceeding any previously developed technology. Quantum computers have now surpassed their theoretical origins, moving beyond the confines of university laboratories to actively process real-world data and resolve complex problems. Their impact is about to revolutionize our methods for cosmic exploration and discovery. In early 2025, researchers announced a significant breakthrough in quantum error suppression techniques. While the intricate technical specifics are less critical than their implications, these advancements enable these machines to perform longer, more stable calculations without succumbing to noise. This improved stability allows them to simulate molecular interactions, optimize intricate logistical networks, and, most importantly for the narrative at hand, process astronomical data at speeds that render traditional supercomputers comparatively sluggish. NASA's Quantum Artificial Intelligence Laboratory is actively evaluating potential applications in planetary science and exoplanet atmosphere modeling. The European Space Agency is exploring the use of quantum algorithms for signal processing in radio astronomy. This is no longer a realm of science fiction. It is becoming an integral component of our technological infrastructure. This development holds profound significance for endeavors such as the 3I Atlas mission. The analysis of astronomical data using conventional methods is an arduous and time-consuming process. Vast quantities of images, spectral data, and radio signals are collected. Subsequently, months, and sometimes even years, are dedicated to running pattern recognition algorithms, filtering out noise, identifying instrumental artifacts, and cross-referencing against existing catalogs of known celestial objects. A single high-resolution observation from the James Webb Space Telescope can require weeks of intensive processing and validation. The fundamental bottleneck extends beyond sheer computing power. It lies within the inherent architecture of classical computing itself. This architecture operates by executing billions of sequential operations, akin to reading a book one letter at a time. Quantum computing, in contrast, does not proceed sequentially. Instead, it explores multiple possibilities concurrently. It can simultaneously evaluate thousands of hypothetical signal patterns, collapsing to a single answer only when a match is identified. What might have previously required 6 months of analysis by a graduate student could, theoretically, be processed in a matter of days, or even hours. This development empowers amateur astronomers who gain access to cloud-based quantum platforms, which are beginning to become available. They can now perform analyses that were once exclusive to institutional resources. A high school student in Jakarta could, for example, rent processing time on a quantum computer and sift through archived SETI data, searching for patterns that human researchers might have overlooked. The democratization of analytical power is already underway. Consider a scenario that should be a cause for concern. A private quantum computing startup, let's refer to them by a trendy moniker such as Qua Analytics, offers a service to analyze archival comet data. They employ a proprietary algorithm that claims to detect non-random patterns in outgassing behavior. Someone then uploads all available observations of 3I Atlas. The algorithm flags a recurring pulse in the infrared emissions, an anomaly that, to an untrained observer, might appear to be a deliberate signal. The company subsequently publishes a blog post featuring charts and graphs illustrating their findings. This information rapidly goes viral across social media platforms, and news organizations pick up the story. Within a mere 12 hours, millions of people become convinced that evidence of a probe within 3I Atlas has been discovered. However, the analysis was flawed. The algorithm misinterpreted instrumental noise as a genuine signal. By the time professional astronomers refute these claims, the narrative has already been firmly established. This is not a matter of speculative fear-mongering. False positives in signal detection are a common occurrence. The well-known WOW signal from 1977, for instance, was never conclusively confirmed. The periodic dimming of Tabby's star was initially hypothesized to be evidence of alien megastructures, but was later attributed to dust. More recently, the announcement in 2020 of phosphine detection on Venus was subsequently challenged by multiple research teams who reanalyzed the data and identified calibration errors. In each instance, the initial announcement generated considerable excitement, followed by widespread skepticism, and ultimately, a quiet retraction that garnered significantly less public attention. The reputational damage extends beyond the individual researchers who made the error. It erodes public trust in the scientific enterprise itself. Now consider the impact of quantum speed on this cycle. If errors occur at 10 times the rate, does public trust diminish at a commensurate pace? The draft protocol stipulates that no party should transmit a reply to a confirmed signal without international consultation. However, what if independent actors, empowered by quantum technologies, decide to respond unilaterally? What if a crowd-funded collective announces their intention to transmit a message to 3I Atlas before the IAA subcommittee has even convened? The acceleration of detection capabilities has a direct impact on governance. Let us specifically revisit the 3I Atlas mission. The peculiar characteristics of the object's tail, which set it apart from Boris, were its fluctuating luminosity and spectral signatures deviating from typical cometary patterns. One hypothesis suggested it was breaking apart. Another pointed to an unusual mix of volatile compounds. A select few harbored the suspicion that something more profound was at play. Traditional scientific analysis would have required many months to explore these theories. However, quantum-accelerated analysis offers the ability to re-examine this data, simultaneously evaluating thousands of potential fragmentation scenarios, thereby either validating the mundane explanation or elevating the anomaly to something far more remarkable. The crucial question remains: will sheer speed lead us to the truth, or will it foster an unwarranted sense of certainty? Part 15. Accolades and the Framework of Trust. On the 7th day of October in the year 2025, the Royal Swedish Academy of Sciences bestowed the Nobel Prize in Physics upon 3 individuals for their pioneering work in superconducting quantum circuits. Their names hold less significance than what they symbolize. They represent the zenith of scientific validation, the highest form of recognition, the institutional endorsement that transforms niche research into worldwide acclaim. And with that recognition comes financial support, influence, and the power to mold public perception of what constitutes reality. Awards are more critical in the scientific landscape than we readily acknowledge. They are not merely decorative accolades. They are structural components. They dictate whose opinions are valued and who commands attention. They influence which academic centers attract the most promising students, which research endeavors secure funding, and which voices dominate discourse when an extraordinary celestial event occurs. When an astronomer affiliated with a Nobel-awarding institution declares a celestial body to be merely a comet, the public readily accepts their assertion. Conversely, when a researcher from a modest university in Kazakhstan posits that the same comet might be something extraordinary, their statement is often overlooked. This phenomenon is not a matter of clandestine plots, but rather of social dynamics. Credibility is cultivated through established networks of trust, and these networks are intrinsically linked to prestigious institutions. The International Astronomical Union, NASA, the European Space Agency, the Max Planck Institute, Caltech, and MIT are pivotal in shaping consensus, verifying data, and establishing the definitive narrative. When an object like 3I Atlas emerges, one that defies conventional models, the established explanation becomes the focal point of contention. It is imperative to understand the implications. When the James Webb Space Telescope captures an image, or when the Hubble telescope detects an anomaly, the resultant data undergoes rigorous institutional scrutiny before being presented to the public. This includes calibration checks, cross-referencing with existing databases, and peer review processes that can span several months. This is not an act of suppression, but rather a demonstration of thoroughness. However, it also means that the initial interpretations of such phenomena originate from within these established institutions, from individuals possessing the requisite credentials and the prestigious Nobel Prizes adorning their offices. But what transpires when these institutions diverge in their assessments from independent researchers? What occurs when a private astronomer, unaffiliated with any formal institution, analyzes publicly accessible data and arrives at a dramatically different conclusion? The draft protocols we have deliberated upon emphasize openness, accessible data, and oversight by specialized committees. These are commendable principles, yet they presume a universal agreement on the interpretation of the data. Historical precedent suggests otherwise. Consider the ongoing discourse surrounding unidentified flying objects, which has undergone a significant transformation in the past 5 years. For many decades, mainstream science consistently dismissed UFO reports as instances of mistaken identity, elaborate deceptions, or psychological anomalies. The chasm in credibility was immense. Subsequently, the United States government released Navy footage depicting unidentified aerial phenomena. Abruptly, the conversation shifted, not due to a sudden increase in the persuasiveness of the evidence itself, but because the source of the information gained legitimacy. An official Pentagon disclosure carries far greater weight than a civilian video, even if the visual content is identical. Now, envision this dynamic playing out with 3-eye Atlas. Suppose the object makes its closest approach in late 2025, and an individual captures an anomalous signal. A private researcher, possessing access to a medium-sized telescope and quantum-accelerated analytical software, publishes a paper asserting that the signal is not of natural origin. They disseminate this research online, circumventing the traditional peer review process. Within a matter of hours, the findings gain widespread traction. The media seizes upon the story, igniting a surge of public interest. Then, 3 days later, a collective of institutional astronomers issues a statement. They have scrutinized the same data, concluding that the anomaly is an instrumental artifact or a natural phenomenon, with nothing further to investigate. To whom does the public lend its belief? The solitary voice or the unified chorus of established authority? The answer is contingent upon the manner in which the message is conveyed. If the institutional response is perceived as defensive, if it is delayed, if it invokes secrecy or restricted data, then public trust erodes. Questions arise regarding the reasons for the delay. What are they concealing? The protocol's emphasis on transparency is designed precisely to avert such a breakdown of trust. However, transparency is effective only when all parties adhere to the same established rules. This is where the situation becomes ethically challenging. The protocol confers authority upon specific bodies, such as the IAA Committee on SETI, the United Nations Committee on the Peaceful Uses of Outer Space, and various national space agencies. These entities function as gatekeepers. They determine when information is sufficiently credible for official dissemination, when consultation is warranted, and whether and how humanity should respond. However, gatekeepers invariably create bottlenecks. And when the public suspects that information is being controlled, even for justifiable reasons, credibility becomes a contested territory. We have witnessed such scenarios unfold previously. In 1996, NASA announced the potential discovery of evidence for microbial life within a Martian meteorite. The announcement was made at a press conference, commanding global headlines. Subsequently, the evidence faced scrutiny. Other researchers identified non-biological explanations for the features observed in the rock. The narrative subsided, but the initial announcement had already shaped public perception. NASA's credibility suffered, not because their findings were incorrect, but because the announcement was premature. Fast forward to the present day. Social media platforms accelerate the dissemination of information. A claim does not require peer review to achieve viral status. It merely needs a compelling narrative. And when it comes to extraterrestrial objects, the narrative is almost self-generating. A mysterious visitor from beyond. Uncharacteristic behavior, official reticence, and independent researchers alleging a cover-up. It resembles a suspenseful plot, and the public is predisposed to believe such accounts. The credibility of established institutions becomes the sole bulwark against the proliferation of misinformation. However, If this credibility is undermined by perceived secrecy or sluggish response times, this protective barrier crumbles. Therefore, let us engage in a hypothetical scenario. 3 Atlas completes its transit. Multiple independent observers detect anomalies, some from institutional sources, others from private individuals, and some utilizing quantum-accelerated technologies that yield results faster than conventional peer review can process. A battle of narratives commences. One faction advocates for the designation of a probe, while the other insists it is a comet. The protocol is intended to mediate this dispute, but it presupposes coordination, consultation, and consensus. What if consensus is not reached expeditiously? What if the interval between detection and public disclosure is measured in hours rather than months? And here lies the question that profoundly concerns me. If the protocol's authority is intrinsically linked to the strength of the institutions that uphold it, and if public confidence in those institutions is already precarious, then what will be the consequences when the protocol is genuinely invoked? When an individual must address the public, announcing a confirmed extraterrestrial contact, the verification of an artificial object, or the initiation of response protocols, who will represent humanity? The Nobel laureates, the delegates of the United Nations, or the live streamers commanding millions of followers? In the coming weeks, we will have our answer. 3 Atlas is already observable. Telescopes are actively tracking its trajectory. Data is being meticulously collected. The protocol remains poised in the background, prepared to be activated should an observation transcend the boundary, from intriguing to definitively confirmed. The world is observing, the institutions are preparing, the independent researchers are honing their instruments. And somewhere within a server farm executing quantum algorithms, a pattern recognition system is meticulously sifting through terabytes of data, searching for an anomaly. When the stakes are cosmic in magnitude, credibility is not an optional component. It is the very arena of contention.